Good afternoon, everybody. Welcome to our annual symposium in our Herbert Irving Comprehensive Cancer Center, an event that we look forward to with great anticipation. And I hope you enjoy the proceedings this afternoon. While we have people in person and more will be joining, we're also live streaming, and I understand a lot of people are joining us in that medium. So to welcome us, I'd like to reintroduce Dr. Katrina Armstrong, the Dean of our medical school, CEO of our medical center, and EVP for health sciences at the university. Thank you.
Neil, thanks so much. I have to say, one of the best things about my world right now, and you guys may think that that means my world isn't full of joy, is that I'm now on my second go-round for most of these things. So it's just so great to be here, to see everybody and to see the community, both here in person and the community online. You know, Neil, when you all invited me to do this, I had a couple of things I've been thinking about as I walked over here and as I've been thinking about the symposium over the last several days. I do just want to say that I think both here at Columbia, both at in the Irving Cancer Vision here in our cancer center, that we're hitting a point in the commitment to collaborative science that I think is beyond what I've seen for an incredibly long time. I think that comes for lots of reasons. Raul will say it's because finally everybody appreciates the need for large data and how we bring those data together, and that actually computation has become a language that we all believe in now. It's not something that you outsource to a paragraph at the back of your grant. I think others will say because I think cancer has led in understanding how a scientific discovery can transform patient care. I mean, cancer has been the place in medicine that's done that, that more and more people are eager to understand that trajectory, to whether they're interested in the brain or the kidney or in fundamental transcription. They're looking to cancer as the model for impact. So we're bringing people out and together from all sorts of different places. I think the third thing that I'll say, right, and you know, I'm going to say this in two ways, so it's a two-part thing, just so to be clear, is one of the reasons that I ended up in cancer research. In fact, the reason, I'll tell you guys the story about why I ended up in cancer research, and it's not a glorious story, let's to be clear. When I finished my training and I decided I wanted to work on genetics and delivery and disparities, my husband is a GYN oncologist. And I discovered that he was always in the OR. And the best way to get to see him was to write grants that he could be on. So I spent most of my early career writing grants on ovarian cancer, and Neil knows this, and endometrial cancer and cervical cancer. But what happened then is, because I'm not an oncologist, just in case you guys don't know, but what happened then, and this doesn't happen now, I think, as much, maybe, is that when I would meet somebody and they would ask me what I did, I started saying that I studied cancer, that I was a cancer researcher. And what I discovered, and what you all know, is that there is nobody whose life, whose family hasn't been affected by cancer. And so I started to understand that cancer, in a way, was this universal, of course, tragedy, but this universal language that was bringing science together with the public. Does that make sense? If we understood that science could make a difference, and we believed that collaboration was going to happen, that cancer was the way that people saw it become real in front of them. And I started after that because of a mentor, actually, Neil, I don't know if you must have known John Eisenberg when he was at Penn. So a mentor I had at Penn who used to tell me that if you want to know whether or not you're doing the right thing, ask your taxi driver and try to explain it to your taxi driver. And it's actually a really good lesson, I will say, that I carry forward with me. Because if you can't explain to your taxi driver why you're doing what you do, it's kind of a litmus test, I think, for lots of things. So I came here because Anil said this is the era of team science for the Irving Cancer Vision, for the Cancer Center. And I just want to echo that I could not believe that more. And I think that's not only because of the power of the science that you all are bringing together, but it's because of the impact that we can have for all of those people. The last thing I want to say, and then I'll obviously turn it back to Anil, is that we welcomed a new president to Columbia in July, a woman named Manoush Shafiq, an economist. And one of the first things that she has asked and done, as Anil and I have presented and talked about this, is asked us to think even more broadly about how we can pull together a comprehensive vision for collaboration across Columbia for ensuring that we're bringing all of the strengths, leveraging all of the talent at Columbia and at our collaborating institutions to take on this most important challenge. So this is the time, I truly believe, for Columbia, for cancer, and I hope for our scientific community more broadly, to be able to think differently about how we do science, how we have an impact, and how we are all able to tell our taxi driver what we're doing actually matters. So Anil, thank you so much. It's such a great time for this. I'm really delighted that you invited me here. Thanks, Anil.
Our Cancer Center, in collaboration with many disciplines across campus, across the university and other institutions in New York City and beyond, is truly dedicated to the continuum from discovery science to translation to investigator-initiated clinical trials to enhancing standard of care to our population science, community implementation. And at the end of the day, all of this needs to converge on enhancing patient care and accessibility for all, no matter what their backgrounds may be, to the latest diagnostics and treatments. And to enable that effort we have a community advisory board, as well as a patient and family advisory council. So I know you'll be delighted to hear the perspective of our patients and community members through Monifa Mott first, and then Mike Furman. Thank you.
Good afternoon, everyone. My name is Monifa Ma'at, and I would tell my cab driver that I am a creative, a community change agent, and a community health advisor. And I am here today. First of all, I want to, before I do anything, I want to say thank you to Dr. Anil Ruskji for inviting me to be here and be a part of the Patient Family Advisory Council. Very important work in asking me to serve on this board, and I have prepared remarks and I'm going to read them because it's important. I also want to thank Mary Beth, who is the engine behind a lot of our community outreach and collaborative initiatives as well. And I personally, I see that, and we as an institution, I represent the Otto Foundation. I'm the Director of Community Health and Special Initiatives at the Otto Foundation. And we've had the good fortune and the honor of working with our research co-collaborator, made possible by the Herbert Irving Comprehensive Cancer Center, and that is Dr. Allison Taylor, and the community-based participatory research program that we work on together. And I'll speak briefly about that. And I want to recognize also Kazim Abdul, who serves a major role as part of the CBR team that we depend on as much for compliance as we do for his easy smile, for those of you who know him, and calm manner. And also the brilliant and humble administrators, Nicole Bain, Kim Burke, Ivy Farley-Cook, Milagro Peters, Maya Lipsman, and the list goes on. I don't want to leave anyone out. Of course, also Dr., who I will speak about later, who is the new Director of Science for the Community Outreach and Engagement, Dr. Christelle Villefranc. These are the individuals that make this office tick and run like a well-oiled machine. And when I reflect as a community member about my experience as an inaugural Community Scientist Institute certificate graduate, yes, graduate, because I completed that certificate. I think about how I began my work as a high school programs educator at, and I'm going to say it, DeVry College. I was educating students at the time about STEM careers and learning about the fun role of being involved with these careers, and as also the official facilitator of Her World, which was an initiative all about introducing girls in New York City, high school girls, to tech careers and robotics, and helping high school students appreciate careers like health information technology, biomedical engineering, infotech, and much more. Well, that ended in 2012. Fast forward to SEM, Scientific Enrichment Month, Herbert Irving Comprehensive Cancer Center again, and Columbia University invited me to participate as a coach in the SIM program with our director then, Irving. And I was responsible. First of all, the experience was incredible. It was my interest, and it still is, and near and dear to my heart in helping young students to become aware of research that exists surrounding the relationship between nutrition, what we eat, how we eat, and physical activity, lifestyle behaviors, and cancer incidence, mortality. And the research has shown us that many metabolic and chronic diseases begin in the gut. So this has been my interest. I had 30 students, and it was very fulfilling for me just to watch them grow and to ignite their curiosity about the connection between science and how we live. And their PowerPoints were amazing, just incredible. And just to watch them, care and become interested in science and how the world works and how their body works. So now we go to the community-based participatory research program, and that's the Otto Foundation, whose mission is aligned with creating sustainable community health solutions to the empowerment of women and girls. Well, it was founded by Martin Otto in 2017, and when he went home in 2016, he found that there were no toilets and showers, and then he created toilets and showers and a sustainable water source, and that was great. That was phase one. Then COVID hits. So during the COVID crisis, the mission morphed into creating and advancing more sustainable health solutions, not just in Ghana, but here in New York City and throughout the continent of the United States in real time. And so we saw, as a result of COVID, the inequities that exist in the healthcare system that the pandemic exposed, and immediately we pivoted and became aligned with local initiatives and institutions like CBPR, the Community-Based Participatory Research Program, and HICCC. And it was in the advent of our beloved Black Panther, Chadwick Boseman, passing from colorectal cancer and the impact on his wife and family and community of fans, many of them women, we decided to collaborate with Dr. Allison on studying about colorectal cancer and determining the knowledge, the attitudes, the perceptions, and the screening habits of Black and brown men in colorectal cancer, with the purpose of understanding and eventually overcoming the barriers to screening and treatment while exploring new modalities and protocols that would lead, that's phase two, that would lead to better outcomes. So the first phase we learned through CBPR was, let's determine the knowledge, the attitudes, and the perceptions. And then once we get this data, determine what can be done to change the course of this devastating disease that is disproportionately impacting so many people in our communities. And then the Patient and Family Board, I'm giving you colors, the Patient and Family Advisory Council. As a certified community health advisor, director of community health programs, and community change agent, I answered the call from Dr. Ruskji to join the Patient Family Advisory Board to bring together patients, families, staff, and clinicians to enhance the experience of medical care for all people, increase cultural sensitivity, and to leverage our experience as patients and caregivers to evaluate current and future strategies that would improve the quality, the safety, and the outcome of patients, because it's really all about patients. Patients are the beginning, they're the middle, and they're the end. They're the reason why we are here. And we must never, ever forget that the source of our research and the stimulus for why we do what we do is to help the people. What I want to have contributed to the conversation and to future initiatives is to work at simplifying and systemizing a sustainable protocol for translating information from the researched to the researcher, from a patient-oriented standpoint in a way that consistently delivers better health outcomes for our community that has long been overdue for systemic change. I could say more, but I just want to sincerely thank you for this opportunity. And yes, you're going to hear from Michael, my co-presenter, who will talk about clinical trials. Thank you so much.
It's tough to follow that. I'll be very brief. My name is Mike Furman. I'm involved with the Patient Advocacy and Family Board. I'm also on the Columbia Cancer Advisory Council. I don't want to talk about any of that. I'm a current patient of a clinical trial here at Columbia. I'm in week 241, so that's, I did the math this morning, that's a little over 4.5 years. You'll be hearing a lot about science today. I won't be talking about any of that. I just want to give you my perspective just as a patient. I'm here every 3 weeks. I was here last week, and I don't know if I see anyone I recognize just yet, but you can usually find me waiting for my lab results. I'm sitting at the coffee shop at Starbucks, and I'm buying yet another Columbia sweatshirt. I didn't attend Columbia. I never have gotten into Columbia, but I proudly wear a lot of Columbia gear. I'll be 59 in a month and a half. I'm a husband of 34 years. I met my best friend when I was 19 at St. John's University. Not quite Columbia. When we were 19, we have 3 amazing children. I'm an uncle, a son, all those things. And I've been fighting cancer since 2011. And it's bladder cancer. I was being treated at Memorial Sloan Kettering. It was unique for someone of my age, my lifestyle, to have this kind of aggressive bladder cancer. I came to Columbia in 2015, and I was in a clinical trial with Dr. McKiernan, and we got some great results. But it's a very aggressive cancer, and it came back in 2017, and I had pretty catastrophic surgery. I'm wearing my clothes. I won't take my clothes off for you. If I took my clothes off, you'd see. So I had my bladder removed, a third of my colon removed, parts of my small intestine. Somehow Dr. McKinnon was able to attach those things to my kidneys. And here I am standing before you. I should have mentioned velocity, but I exercise a lot, still to this day. I'm able to do those things. After that surgery, there was some cancer that was in my outside of my bladder, so I went through some very tough chemotherapy. We thought we were clear, and then in 2019, the cancer again recurred, and it was in my lymph nodes. Very dangerous. It's late-stage bladder cancer. I mean, the best way I can describe it, and I want to give you a feel for it, you know, as a patient, is that you're on a railroad track, and you know the train's coming at you, and you see those lights, and if there's nothing else that can concentrate your mind, that's it, you know. So I talked to Dr. McKiernan, who, if you don't know him, is a genius, obviously. We all know. He's one of the most inspiring people I've ever met. And he introduced me to Dr. Drake here at Columbia, and introduced me into a clinical trial involving an immunotherapy that had a vaccine component. It was synthetic DNA that is injected through electroportation, which basically, again, I'm not a scientist, I'm just a person. It's shock treatment, and it's pretty intense. But my cancer is in check. I've had very clean scans for now several years. And again, that being on that railroad track, and when you face your own mortality, it concentrates your mind, and you think about what you can do while you have this gift of life to do for others. So that's my interest, personal interest in supporting Columbia and clinical trials, and I'm being obviously very selfish because this happened to me, and I want to help others. It's my cause. But you know, the broader perspective, if you can just allow me to sort of share this with you, is that every 3 weeks I'm in the waiting room, and I'm at the cancer center, and I ride the elevators, and if there's nothing more leveling than cancer. It is a very leveling experience. There is no discrimination with cancer. Every person is represented in that sense, because cancer doesn't discriminate. It goes after everyone. It doesn't matter what your gender is, your race, your age, your socio. It doesn't matter. It is, and in that sense, it's very interesting to me, and it's important, I think, just to echo what Manifa had mentioned, that in clinical trial studies, we engage the community to make sure that we have a very diverse pool of patients that enter into clinical trials, so that we can get better results, better science, better indications, and we learn more. So in the outreach that Monifa had mentioned, I triple that. I mean, I wish I can yell, but I can't, and I shouldn't. But that is so important to do. So thank you for what you do. I love the concept of trying to explain all this to a cab driver. I don't know that I could do more in explaining my successful so far clinical trial experience, except to say that it's incredible that scientists could come up with DNA strands in a lab, mimic the cancer cells and the proteins that attach to my cancer cells, and tell my T cells, go after those guys, they're bad guys. It's just incredible that technology, and I've lived long enough now, 13 years in my cancer journey, to be able to sort of ride the wave of your innovations. So keep doing it. I think that we're on the cusp of doing really great things. I'm the beneficiary of living long enough to see all this happen, and I want to thank all of you for attending today, listening to at least my story and to the science. That's far more important than what I have to say. Thank you very much.
Thanks to both of you for truly inspiring words. Thank you. So our mini symposium is set up to be a series of 5 vignettes, each of them touching on the conceptual framework of cancer research and therapy. And I hope you enjoy what we're thinking about now, but even more so what we're thinking about the future and where we possibly could be in the future. So each vignette will have an introduction and a talk or talks. So the first vignette's on are really exceptional efforts in clinical trials on campus, but providing leadership in diversifying our patient population that are recruited and enrolled into our clinical trials, both investigator-initiated and industry-sponsored. So overseeing the session will be Dr. Jide Williams, Professor of Neurology and Vice Dean of Community Health. Jide?
I just want to first thank you, Anil, for having this incredible symposium, putting this all together. But I just want to just especially thank Monifa and Mike for being here today and for sharing your stories and for your commitment to cancer research and clinical trials. Mike, you're extremely brave, extraordinary individual. You've inspired all of us. And I'm especially moved by your commitment to making sure that all groups benefit from access to clinical trials. So I'll be talking a little bit about our initiative to improve diversity in clinical trials. And so, you know, as we know, there are truly disparate health outcomes, not just in cancer, but across all clinical trials in medicine. And a lot of it's been driven by a number of interacting issues related to distrust of the medical community for many historical and existing reasons. The lack of diversity in the trainee pool, the lack of diversity among our trial investigators themselves, and the lack of diversity among trial participants. And to the last point, participation rates of ethnic minorities are tragically low. Even though they make up 38.7% of the US population, they represent 2 to 16% of clinical trial participants. African Americans participate at rates less than 5%, and our Latinos only 1%. So when you unpack these disparities, you start to unveil barriers across multiple sites. And we often talk about the barriers related to the patient. We often talk about awareness and distrust and the financial burden and other social determinants of health and the inconvenience. But we're finding more and more that a lot of these challenges are also in-house. They are the site-related barriers, our outreach, which tends to be limited, our lack of standardized screening processes, our lack of referrals from community sites, and our lack of resources and challenges around leadership, specifically in this area across the country. At the provider level, again, there's lack of awareness of the available trials. You know, everybody's pressed for time and RVUs and productivity targets. And so the lack of time to discuss these trials, some providers are frankly uncomfortable with communicating about these trials. And then there are other biases, implicit biases related to our efforts to recruit more minorities into some of these trials. So The good news is that there are cancer centers doing a really good job, albeit with room for improvement, and really focusing on increasing the enrollment from underrepresented groups. And I'm so proud of this cancer center under the leadership of Dr. Rusky to share that, 40% plus of clinical trial enrollees here are from underrepresented groups, which is one of the highest, if not the highest in the country. And it's one of the reasons why our cancer center has been recognized. A recent visit by the current First Lady, as Jill Biden, as well as the Queen Letizia, really highlighted at a recent visit here the importance of diversity, equity, and inclusion programs in our efforts to end cancer. And so we have a justice framework here at Columbia that we are applying to our efforts to increase diversity in clinical trials, and it really begins with a relationship. The relationship not just with our patients, but with our communities. And the relationship needs to be sustained, not episodic or sporadic, but sustained and ongoing, and it needs to be bidirectional. And those relationships need to encompass more than just a specific research study and goals. They need to be true bidirectional relationships, and that's why that is at the bottom of the pyramid. And that relationship needs to be sustained across the entire arc of research participation. Inclusive design is another very important item to address, and even once you've established these strong, robust relationships, it's critically important to pay attention to inclusivity, to make sure that our inclusion and exclusion criteria do not disproportionately disadvantage certain groups over others as best as we can and as much as the science allows. And then accessibility is important. Even if you have an inclusive design, you also need to make sure you have an accessible pathway to inclusiveness in specific studies. And these range from, things that we might overlook, like transportation, financial barriers, and other social determinants of health-related challenges. Fit is also important to consider. Even if your trial is inclusive, it's accessible, is it a good fit for participants, and is there mutual alignment, not just from the side of the investigator, but also alignment with the participant in the process of getting enrolled in the clinical trial. And one of the things that we've really tried to do is focus on openness. And that is, rather than, drive specific clinical trials into the community, to try to open the community's acceptance of participating in research in general. So make research that social norm, that cultural norm. Open up the community's minds to accepting clinical trials, and not just trying to ram through one or two specific clinical trials. And so it's really important for us to broaden our targets, our goals for our communities, and really have them be much more open to participation. And the final stage in the framework is readiness. So there are major initiatives here at this cancer center. The National Cancer Institute's MUN Corp initiative. This is for minority and underserved oncologically research program. This focuses on the best cancer care for underrepresented minorities, the population that surrounds this center. The Clinical Trial Navigator initiative to really help patients find and understand the clinical trials. It's really can be a complex landscape to navigate successfully, and Clinical Trial Navigators are very, very helpful, and the center has invested heavily in those folks. And then our Columbia-Pfizer initiative in clinical trials diversity, which I'll touch on briefly. And so this is a new initiative that started established in 2021, And it has 5 broad domains. One is to increase the diversity in the trainee pool to develop the next generation of clinical trialists. 2 is to develop sustainable health capacity in communities. 3 is to really build awareness about clinical trials among people of color by leveraging digital strategies and working with our community to co-create and deploy these innovations, and then bolstering representation in academic medicine by really recruiting and retaining diverse clinical investigators. And all of these initiatives are fully ongoing, and we're really excited by the progress we're making across all of these initiatives. I'm just going to touch briefly on the sustainable health capacity communities, and this really addresses the issue of leveraging relationships, trusting relationships, building academic linkages to our clinical trials from the community. And this has really involved not just working to establish community advisory groups to review our clinical trial portfolios, also creating mini-grant opportunities for our CBOs, targeting ideas for diversity in clinical trials and priorities for diversity in clinical trials. And we've also been establishing community physician partnerships in small and large groups, as well as federally qualified health centers, to really help increase that openness to clinical trials. And one of the things that we've been doing is we're really working on a model that embeds health educators, community health workers, as well as other health extenders within community organizations, within community physician practices, conducting outreach at these partner sites, facilitating access to our clinical trials, and this integration of these health educators in our community partners has been really welcomed. Actually, the idea came from our community partners who really wanted us to help them shape the culture within their organizations in a way that's more favorable and accepting of research. So I'm going to move along right now and invite my dear friend, Dr. Mary Welsh, who is an associate professor of neurology at the Vagelos, to talk a little bit more about some of the challenges, some of the opportunities and complexities, and some of the wonderful work that she's been doing. Mary.
So I just click here. Right. Okay, great. So thank you so much for inviting me. This is an absolute pleasure. It's a particular thrill to participate in any program involving Dr. Williams. I first met Dr. Williams during my rotations at Harlem Hospital as a Columbia neurology resident. So yes, as a neurologist by training here up before you, but my subspecialty is neuro-oncology. So before that time, my exposure to patient care was predominantly limited to being a research assistant at Sloan Kettering, and also as a medical student at Northwestern. And for those of you who don't know Chicago, Northwestern sits about 2 blocks from the toniest section of Chicago called the Magnificent Mile. So it's not exactly the place you go for racial and ethnic diversity. So coming from this background, as you might imagine, the communities of Washington Heights and Harlem had a lot to teach me about healthcare disparities and socioeconomic determinants of health. You really have only to open your eyes. However, it really wasn't until I left my fellowship, also at Sloan Kettering, and I started my first job that I truly became engaged with today's topic. I took a position as the second board-certified neuro-oncologist ever to set up shop in the Bronx. And my partner in this endeavor, he claimed the title of the first, and he was only a year ahead of me in training. So we were both young, sort of, certainly enthusiastic, and quite naive. So we both had completed our training at Sloan Kettering, and you've already mentioned Sloan Kettering, and as I think you all know, this is a private hospital. It's devoted exclusively to cancer, and it's situated in the Upper East Side. And that is a neighborhood with the highest median income in New York City, which means it's among the wealthiest in the world. And MSKCC produces outstanding preclinical and clinical research. There's no fault there, but they really have little standing when it comes to diversity research and disparities. And its patient population is overwhelmingly white, and with rare exceptions, they are blessed with very good insurance. You really need it to get into Sloan Kettering. So in contrast, if you go sort of 10 miles north, I guess, you hit the Bronx. And the Bronx residents are predominantly Hispanic, and the map shows that in yellow, and Black, and that's shown in green. And a very small patch of blue is representing Riverdale, okay? So depending on your age and your interests, you might think of the Bronx as home to the Yankee Stadium or the Botanical Gardens, J-Lo, and I had to, in honor of Dr. Williams, of course, had to mention that Bronx is also considered the birthplace of hip hop. And of course, those of you who don't know, Dr. Williams, one of his major endeavors is hip hop stroke, which basically leverages this music to educate children about stroke, which is incredible. So these cultural gifts aside, the Bronx also has its share of problems. And these few images from New York City's 2018 Community Health Profiles map highlights those disparities very clearly. So the Bronx is home to the poorest urban congressional district in the country. And in this map, I think on the left, you can see the dark blue indicates that 26 to 45% of residents live in poverty. And not unrelated, as we know, residents also suffer from high rates of HIV/AIDS, and that's sort of the middle map, and as well as diabetes, obesity, asthma, and high infant mortality. Death rates are also up to 30% higher than in wealthier neighborhoods, and the map I thought to the right is particularly troubling. It shows how premature mortality, that is, death under the age of 55, disproportionately impacts this community. It's pretty horrific. So there we were, a very white neuro-oncology division of 2 in the middle of a predominantly brown community. And we started to do what neuro-oncology divisions have to do. We built a trial portfolio. And in neuro-oncology, access to clinical trials is absolutely essential, and that's not just for posterity or science or even your academic career. It's simply that in most of the diseases we treat, there are no good standards of care. They just don't exist. So to give you a little perspective on that, this is the NCCN guideline from 2015 for glioblastoma, which is among the most lethal forms of cancer. Basically, your options after you progress through first line of treatment are that you can cut out more tumor, and you can go on a drug called lomustine, which was FDA approved in 1976, which is the year of my birth. You can enroll in hospice, or you can enroll in a trial. And so we built that clinical trial portfolio. We built it, and no one came. So I was at Monty for 4 years, and though I had written 2 papers on primary central nervous system lymphoma during my fellowship, I didn't actually see it as an AIDS-defining illness until I got to the Bronx, right? I also treated 3 patients who not only had to contend with glioblastoma, but also with HIV. And this is a comorbidity which until recently was almost always universally listed as an exclusion for any clinical trial. So they're not getting in a trial just because of that. And I learned a tremendous amount from an incredible set of colleagues, and many of them were deeply, deeply committed to this community. And I fully absorbed, I think I did, one glaringly obvious lesson in those first 4 years it's been attending. As bad as cancer can be, and we all know it's bad, it's made worse by poverty. And of course, poverty in New York disproportionately impacts communities of color. And you can see that here. As shown on the left, you have the low household income key, really pretty well maps onto the yellow and the green areas of the Bronx. So how did we fare in the Bronx with our clinical trial portfolio and our enthusiasm? Not so great. We created a portfolio of 12 trials, and we enrolled 4 patients. So that is a rate of 1 patient per year. So after my partner took a job in Seattle, I came back to Columbia. Andy Lassman recruited me. And here I'm pleased to report that I've had slightly more success in that. But disparities, unfortunately, they don't disappear once you cross that Harlem River either. And while Washington Heights may not be the South Bronx, it is also a very far cry from the Upper East Side. And one of the greatest strengths, I think, of this institution is its diversity and its commitment to that. And in my practice now, I care for patients, yes, from well-heeled communities in New Jersey and Westchester. But the vast majority of my patients come from Washington Heights, from Inwood, from Harlem, and yes, the Bronx. So I thought I would tell you about one of them, just to get a feeling for some of the challenges, right? So EP, because we have to be HIPAA compliant here, she's a 47-year-old woman. She's Spanish-speaking only. She's a mother of 2. And she presented to our ER with aphasia, which is basically a difficulty expressing yourself, as well as some imbalance and falls. And 2 years prior, while living in the DR, she had palpated a mass in her breast, and she had been diagnosed with breast cancer and received standard treatment. So if asked to sort of self-identify according to categories that we actually use in our national cancer statistics, she probably would have called herself Hispanic, right? And that actually would have entirely ignored the high likelihood of African ancestry, which is characteristic of many patients in the Caribbean, an ancestry that might have had relevance in her case, as it's associated with a heightened risk of triple-negative breast cancer, which is much more prevalent among Black women. And this subtype, unfortunately, which she had, also has a very strong predilection for brain metastasis. So, of course, that's what her imaging showed on presentation. So I don't think you need to be a radiologist to realize there's something wrong with these images. She's got brain metastasis. So we gave her some steroids that reduced the swelling around these tumors. She got better, sufficiently enough to have a conversation about what her goals were and what she wanted, and we were very aggressive. She's 47 years old, she's got 2 kids. So she actually underwent 2 craniotomies in a span of 3 weeks, and she had all her other areas of disease treated with gamma knife, which is basically a highly focused form of radiation. She left the hospital, she was actually at her baseline, she did very well. She met with medical oncology, but as she had no obvious disease elsewhere in the body at that time, nothing measurable, she just didn't qualify for a clinical trial. There just wasn't one. Excuse me. So this is not uncommon. So there was an outstanding paper that Dawn Hirschman, of course, co-authored. And in it, researchers examined the trial decision-making pathway. They wanted to characterize and sort of quantify what are these barrier domains. And you can sort of see them listed here, and Dr. Williams mentioned them as well. What they found was that more than half of all cancer patients don't go on trials because no trial is available for that particular cancer type. And when they could, an additional 22% weren't eligible. So put another way, according to this particular paper, structural and clinical factors meant 3 out of 4 cancer patients didn't even have the option of a clinical trial. And of course, that doesn't let us off the hook, right? We physicians are absolutely part of the problem. And if we don't take the time to inform our patients about, all of our patients about the research, we're never going to move this bar. So I do want to take a step back and ask why should you care about clinical trial enrollment? Because it's pretty obvious, I think. They are an absolute requisite to improving cancer outcomes. Everyone, absolutely everyone, wants better, safer, more affordable treatments, but we know that research takes resources. And estimates of the cost of bringing a drug from the bench all the way to FDA approval, it's about $2 to $2.7 billion, billion with a B, and it takes about 10 to 15 years. So that's a very long time, especially in the life of a cancer patient. So how do we speed up that process? Well, you have to reduce the log jams, and it's really clear that the transition from bench to bedside constitutes a major bottleneck. Our inability to effectively recruit and retain patients into clinical trials is just a major problem. And if you want to contextualize this a little bit, 80% of NCI studies don't meet their accrual targets, and 50% close without even minimal accruals. And that's some really painful numbers when you consider the investment in terms of time, patient experience, money, as well as the opportunity costs that go into designing trials and getting them off the ground. So not only are we failing to accrue significant numbers of patients, but as Dr. Williams pointed out, when we do enroll them, they often don't reflect the diversity of our populations. So, as you said, racial and ethnic minorities, they make up about 40%, and a tiny, tiny, tiny fraction of clinical trial participants. So among NCI-sponsored oncology trials, where race and ethnicity data is actually collected, you get about 9% of participants in Black and about 3% are Hispanic. And this doesn't even consider studies in which such demographics aren't even counted. So clearly, we always have to do a better job measuring these things. So I want to pause and just think about this for a second, though, because there's some clinical essay. So clinical research, which we sort of consider broadly, comes in many forms. And when we consider the problems of accrual, specifically minority accrual, it's one thing to ask a patient to donate tissue for research or to participate in mindfulness training, and it's a very different thing to ask someone with a terminal illness to spend 1 day a week of their precious time sitting in an infusion suite, getting a drug that may or may not work and could potentially cause harm. That's a big ask, and it's very different from some of the other things. So investigational oncology trials are really demanding. They demand a lot. And while some patients can benefit from the added monitoring and attention that comes with being a participant, very few drugs actually make it beyond phase 2. And that's a fact that very few patients, I think, fully grasp. So in one study, researchers asked patients to give sort of a ballpark estimate of how they thought they would do. What was their chance of improvement on a trial? And they put it at 50%. And so that's a real optimism bias because we know that less than 5% of drugs make it past phase 1. So when you hear these figures, less than 5%, the question I started with doesn't seem so radical, and we actually have to confront it. I think it's not illegitimate to ask why any oncologist would ask a patient like EP, she's a woman burdened by disease, but she's also hobbled ultimately by neurological disability, poverty, limited resources, not to mention the fact that she has to care for her 2 children. And you're going to say, come here, spend a week getting an infusion, you may not benefit. Something to think about. Nevertheless, there are several reasons why we absolutely need to put in the effort to educate all of our patients about clinical research. It just has to happen. So one of the reasons is that there are some clear biological questions that come up. So for instance, epidemiological data shows that certain populations are just more susceptible to cancer than others. So gastric cancer, which Dr. Gabriel will be talking about, impacts Asians at higher rates. And colon cancer, as we've mentioned, and prostate cancer disproportionately affect Black men. And sometimes, even if the incidence is lower among certain minorities, there are disparities in outcomes too. So on that sobering note, I read yesterday about the death of Tasha Butts, and she was the head coach of women's basketball at Georgetown. And she was only 41. And she's a very visible reminder that breast cancer mortality is highest among Black women year over year over year. And what's going on here? Well, differences in socioeconomic status and healthcare access absolutely play a key role, and I hope I convinced you of that in my sort of Bronx story, right? Culture always matters too, and this is where, Gita, your work has been brilliant, right? It has tremendous power to influence behaviors, diet, whether or not people use certain supplements, or even openness to vaccines. But there are also real genetic determinants at play, right? Examples include cancer driver gene mutations. There are genetic and epigenetic influences on body mass index, on immune response, and there's also genetic polymorphisms that can impact how drugs are processed, right? So the classic example of a molecular determinant, if you will, is the EGFR mutation in certain lung cancers. And historically, this was identified as a disease of young Asian women non-smokers. That was sort of what you would rattle out to your attending if asked, right? That's what the group. But there are now 4 generations of EGFR inhibitors available to all patients, and they're not just all young Asian women non-smokers. And they have substantially improved lifespans and quality of life in this subset of patients. So without diversity across the research spectrum, from the biobank samples used in preclinical models all the way through phase 1, phase 2, phase 3, those who are left out will miss out. And on that note, I would like to introduce the next speaker who will talk to you about some of the latest and upcoming work in precision medicine. Thank you so much.
Thank you, Mary, very much for that great presentation. So a little change of gears, I'm going to talk a little bit about my perspective on diversity in research. So clinically, I'm a gastrologist. I see patients with hereditary GI cancer syndromes, but I also have a lab. And as an underrepresented minority myself, when I see my patients, I see myself and they see me. And so I bring that back to the lab. And I think about the model systems that I use, and I think about whether or not that model system really models my patients. Because many of the preclinical models I use are agnostic to the diversity of the patients that I see. And so I try to use these 3D organoid model systems to capture the diversity of my patients so that I can develop results that hopefully reflect them and can be used in the future for clinical trials. So I want to define for you what the organoids are and kind of how we're using them. So 3D patient-derived organoids are a 3D cell culture technology or technique. And what we do is we take normal or diseased tissue, for example, cancer, at the time of an endoscopy as a gastroenterologist, or at the time of surgery. And we take the tissue, we take it to the lab, and we break it down. We break it down using enzymes, we break it down mechanically, and then we're left with a single cell suspension. And then we embed it in the substance called matrigel or basement membrane of our choice. And then we bathe it in media for several weeks, and they grow these beautiful 3D structures you can see here. And the really cool and important thing about these 3D structures is they really capture the genetic, in many cases, epigenetic diversity of our patients. And so it gives me a very powerful way with which to ask questions with a model system that better reflects our patients. So how are we doing that? So how we're doing that already are using these organoids as kind of a preclinical trial. We can derive these organoids from a variety of patients, from a variety of backgrounds, and then trial therapeutics on them, and then ask the question, is there a difference in response based on genetic background, epigenetic differences, racial and ethnic differences, and also environmental exposures? We're capturing environmental data as well. So I think it's important that we all think about diversity in our research, not just if we're a clinician doing clinical research, but also if we're in the lab doing wet bench research. How are we capturing our patients in the work that we do? And with that, I will ask for questions. With my
So we have time for just one question for the speakers of this section, if anyone would like to ask that question. If not, that's okay too. They'll be around, I'm sure, for the reception. So,
just variation across the boroughs and how you're contending in clinical trials, like Staten Island, Queens, etc.
So I think, so the question is how would you manage diversity across the different boroughs? Well, I think a lot of it comes down to exactly what Jide is talking about. You have to have connections with the community. You have to be able to get your message out there, and you have to be able to have people come in the first place. I think most people, once they're in the room, once they're having the discussion, will be interested in a clinical trial. I really do. I think that the mistrust can be overblown. But you first have to get in the room, and that has to be made a lot easier for patients.
Okay, we'll switch gears, and our next mini session is on genome integrity, reparative mechanisms to attack DNA damage, and what's the future hold in terms of identifying new targets and the therapeutics that may emerge. Jean Gauthier oversees our Genome Integrity Initiative on campus. He's professor of genetics and development. Jean?
So I'll be introducing the theme of genome integrity. Can you hear me? And starting by the very basic fact that cancer is a disease of genome instability. And the development of technologies such as karyotyping reveal the extent of instability leading to abnormal karyotype showing polyploidy, aneuploidy, translocation, insertion, and deletion, as seen here on a panel of a breast cancer cell line. With the extraordinary development of sequencing, we can now get a much higher resolution of this landscape, mutated landscape. And here we have a circus plot from the outside to the inside. You have different level of scale, and outside you can now resolve point mutation, nucleotide variation, as well as small copy number variation, and finally rearrangement. And this is a breast cancer, a BRCA1 deficient tumor cell line. So genome instability is really a hallmark of cancer, as per Hanahan and Weinberg, and that directly or indirectly influences replicative immortality, sustained proliferation, as well as avoiding immune surveillance, which is to some extent linked to the mutation burden. So DNA damage arises from exogenous sources, such as environmental exposure to radiation, as well as endogenous sources, primarily during physiological DNA transactions, such as replication and transcription. And there is a direct link between this damage leading to instability and tumor development that is best demonstrated by the genetic predisposition of patients with germline mutation in any of the DNA repair pathway to develop cancer. Yet the majority of therapies are DNA damaging therapy, whether they are radio or chemotherapies, which first impact is to increase the DNA damage burden and at the same time inhibiting tumor development. And understanding and exploiting this apparent contradiction is critical to develop novel and/or more effective therapies. And the concept of synthetic lethality has been central to the development of such new therapies. In the case of DNA repair shown here, two independent pathways can maintain genome integrity following the damage and mutation in gene of either of these pathways is tolerated. However, when both are inactivated, then we get lethality as shown here. So this is following DNA damage, of course, in the case of DNA repair. And to take an example that is familiar for a lot of people here, in the case of BRCA deficiency, inhibiting poly-ADP ribose polymerase, PARP, leads to synthetic lethality between those two pathways. And this paved the way for inhibitor of PARP inhibitor, which are the poster child of such an approach, basically. It turned out that the actual mechanism of synthetic lethality is not as straightforward as we originally predicted. However, the application of the idea is still fully valid. And indeed, this concept is used in many ways to exploit tumor vulnerabilities and to identify new targets. For example, genome-wide CRISPR screens are used to identify genes that are essential in specific tumor backgrounds, or to identify drugs active against cell harboring specific mutation. In addition, there are other initiatives such as DepMap that helps identify tumor-specific dependencies of unknown origins. So additional approaches and technology are expanding the scope of genome integrity research. This is what we're going to hear a little bit next. And I'm going to mention briefly 3 examples. Mutational signature, for example, can be extracted from tumor genomes and reflect the mutational process involved during cancer development. They can reveal specific signature de novo, they can reveal specific mutational process de novo in tumor sample, or they can identify a signature of unknown origins, and which can be used to track back the origin of those genome scars. So the other point that I would like to make is about protein structure prediction. This has been changing the way we think about protein-protein interactions, for example, or the impact of point mutation in a given protein. And we will hear about that very soon with Rahul Rabadan and Brent Stockwell. Finally, base editing is a quick and high throughput approach to address function of mutation of unknown significance, which constitutes the majority of what people find when sequencing tumor genome, or to identify genetic modifier, and we will hear more about that next with Alberto Ciccia. Here at Columbia, the Genome Integrity Initiative interact closely with the program for mathematical genomics because we deal with large data, and will feed into the Irving Drug Discovery Program, which you will hear about later. In addition, the initiative is developing connection with the stem cell, the RNA, and the human tissue immunity initiative. We all connect eventually to genome integrity. So now I will let the stage to Alberto.
So thank you, Jean, and thank you, Anil, for the opportunity to present our work. So my laboratory is interested in studying the DNA damage response. And central components of the DNA damage response are the ATM and ATR kinases, which are activated by sensor proteins to phosphorylate hundreds of effectors with the help of transducers and to induce cell cycle arrest, DNA repair, and when this is not possible, cell death or senescence. And the DNA damage response is a complex network of physical and genetic interactions, which is enriched in essential genes and large proteins with multifunctional domains. And most importantly, there are more than 40 genetic syndromes they are caused by mutations in genes involved in the DNA damage response. And some of the common features of these syndromes are immunodeficiency, infertility, progeria, neurodegeneration, growth retardation, and also cancer predisposition. And one of the common syndromes caused by deficiency in DNA repair that leads to cancer predisposition is hereditary breast and ovarian cancer, caused by mutations in the genes BRCA1 and BRCA2, and other genes involved in homologous recombination and replication fork metabolism. So BRCA1 and BRCA2 are mutated in more than 50% of hereditary breast and ovarian cancer, and they are also mutated in hereditary prostate and pancreatic cancer, in addition to other tumor types. BRCA1 and BRCA2 deficiency is also frequently observed in triple-negative breast cancer and serous ovarian cancer. And BRCA1 and BRCA2 suppress tumor development by maintaining genome stability. And in particular, they promote the repair of DNA double-strand breaks, or they protect replication forks that are stalled by DNA lesions, and they also suppress the accumulation of single-strand DNA gaps that might originate during DNA replication. And as such, tumors that are deficient in BRCA1 and BRCA2 are sensitive to DNA damaging agents. And most importantly, there are tens of thousands of mutations in BRCA1 and BRCA2, and the vast majority of them, more than 4,000, are variants of uncertain clinical significance. And so this is a big challenge because it can lead to inappropriate clinical management of BRCA1 and BRCA2 mutation carriers, given that we don't know whether these mutations are pathogenic or not. So how do we study the functional impact of mutations and determine whether they are pathogenic or not? So to do that, we utilize genome editing tools, and in particular base editing, developed by the laboratory of David Liu at Harvard Medical School. And these tools rely on an enzyme, Cas9, fused to a cytidine deaminase, ApoBec, which is targeted to specific locations in the genome using guide RNAs, and there induces C to T-based transitions at specific locations. And some time ago, we showed that these tools can generate 32 different amino acid substitutions, and they can also lead to the introduction of stop codons by converting codons the coding for glutamine, arginine, and tryptophan uniquely into stop codons. And we call this approach iStop for induction of stop codons. So in order to study the function of mutations at large scale, we develop approaches to do base editing screens, where we mutagenize the coding sequence of BRCA1 and BRCA2 and other genes involved in breast and ovarian cancer using cytosine base editors. We then treat the cells with genotoxic agents in order to identify mutations that will lead to sensitivity to DNA damage as a result of the disruption of the function of BRCA1, BRCA2, and the other genes. And we can therefore infer which mutations are disrupting the activity of these genes, and they are likely therefore predisposing to breast and ovarian cancer, allowing us to classify the functional variants and determine which one have a likely pathogenicity. Mutations don't really act in isolation, and their pathogenic effects can be influenced by additional mutations. They can either increase or reduce their pathogenicity and act as modifiers. So in our lab, we are also interested in identifying modifiers of BRCA1 and BRCA2 mutations, and we are therefore conducting base editing screens in BRCA1 and BRCA2 cells, mutant cells, in the presence of DNA damaging agents, with the hope to identify mutations that would convert pathogenic mutations into non-pathogenic and non-pathogenic mutations into pathogenic. And this will help us to have a more accurate assessment of cancer risk in patients carrying mutations in BRCA1 and BRCA2. As mentioned by Jean, one of the treatment for BRCA1 and BRCA2 mutant tumors relies on the use of PARP inhibitors, which induce synthetic lethality in cells that are defective for BRCA1 and BRCA2. However, over time, cells treated with PARP inhibitors, resistance can occur in these cells. So it is important to identify additional targets that could be inhibited to induce lethality in BRCA-deficient cells. And many investigators around the world are conducting screens, in particular CRISPR knockout screens, using the Cas9 protein in order to identify vulnerabilities of BRCA1 and BRCA2 mutant cells. And these screens allow us to identify proteins that when they are lost, they lead to a lethality in the absence of BRCA1 and BRCA2. In our lab, we are conducting base editing screens in cells that are defective for BRCA1 and BRCA2. And these screens can allow us to identify mutations that also disrupt proteins, leading to lethality. But in addition, we can also identify mutations that could alter the enzymatic activity of proteins, either by increasing or decreasing their activity, and this could result in lethality in the absence of BRCA1 and BRCA2, or mutations that could impair protein-protein interactions, or they could affect post-translational modifications. And so we think that these approaches will be providing more information about the vulnerabilities of BRCA mutant cells, and we hope they could lead eventually to novel drug targets. One of the issues of drugs is that they often have off-targets, and we don't know exactly what these off-targets are. So by conducting base editing screens in the presence of particular inhibitors, we can identify mutations that could lead to resistance to the inhibitors as a result of mutations in residues that are important for the binding of these drugs. And so this type of screens can allow us to identify drug binding sites, and eventually they can lead to improved drug design. One of the promising approaches for cancer therapy also relies on the use of cell-based therapies, using engineered T cells that can express chimeric antigen receptors that recognize antigens on tumor cells that they can lead to the killing of the cancer cells. So in a project led by the group of Ben Iser in collaboration with us, we are conducting base editing screens in T cells in order to identify mutations that would increase the ability of T cells to kill cancer cells, with the hope to identify mutations that could improve CAR T-cell-based therapies for cancer. Base editing approaches are particularly promising for engineering T cells. And our strategy to induce stop codons to disrupt genes has been recently utilized in clinical trials in the UK to engineer CAR T cells that were subsequently utilized for killing T-cell leukemia cells. And in a clinical trial of 3 patients in the UK, 2 of these patients having T-cell acute leukemia are currently under remission. And so this appears to be a promising strategy for engineering CAR T cells and the treatment of tumors. So we're really excited about these base editing approaches because we think they can allow us to study the function of nucleotide variants and genetic networks for better understanding the function of genes, because they can allow us to define disease-causing mutations and their modifiers and develop novel targeted therapies for improved precision medicine, because they can also allow us to identify small molecule targets and mutations that induce drug resistance for better drug design. And so the base editing work in my lab was conducted by a very talented group of scientists. In particular, this work was initiated by Pierre Billon, a former postdoc in the lab. And base editing screens were then developed by another former postdoc, Raquel Quaya-Martin, in collaboration with a student in the lab, Sam Hayward, and other members in the lab, Giuseppe Leuzzi, Tanita Carr, and Alina Vaitsenkova, are currently conducting additional base editing screens. And we've been collaborated with many members of our community, Chao Lu, Raoul Rabadan, Ronnie Rostin, Yufeng Shen, Ben Iser, Yeller Goblom. and also with Raphael Guerroy, Paris Saclay, and Anshu and MD Anderson. And I will be happy to take any questions.
So one question again for our Genome Integrity presenters, if anyone would like to ask one. Don't be shy, everyone. Anyone got one? No?
And this really approach for base editing and screens could be applied to a number of other tumor suppressor genes, correct?
Yeah, we are focusing mostly on these genes because of our expertise, but it can definitely be applied to any type of genes of interest to identify the functional mutations and also to identify new vulnerabilities for these tumors. Yeah, so we are just using it as a proof of principle at the moment, but there are really enormous number of possible applications. Thank you.
Okay, our next mini session is an initiative across the Cancer Center, across the university actually, that takes advantage of the growth and explosion in computational approaches to protein structure, and then correlating that or marrying that with experimental approaches in protein function. This initiative is being co-led by Brent Stockwell, and our professor and chair of our Department of Biology, along with Mohammed Al-Qarishi, who's assistant professor of systems biology. Mohammed's unable to be here, but this has also been a joint effort with Raul Rabadán, who's professor of systems biology, endowed chair in surgery, and importantly, as a physicist, brings orthogonal approaches to cancer research and cancer therapy as director of our program in mathematical genomics. So we'll turn it over to Raul and Brent.
Thank you very much. Let me see here, I go with this nice picture. So just following up with the previous talk, I mean, one of the things that we're, in the last 10 years, as you know, I mean, sequencing has been changing and the landscape of how we understand cancer. So we see patients, we look at the mutations, the somatic mutations, and typically there are around 100 mutations or more in the patients that are changing the structure of the proteins or proteins. If we look in the whole genome, they are usually tens of thousands. And as Alberto was mentioning, we understand only a few of those. I mean, only 1%, less than 1% of all these mutations. If we are looking in coding, it's a few of those that they have been characterized. Most of them we don't know. I mean, in BRCA, that is a well-studied gene, we only know a function of few of those. In most of the other genes, we don't understand what is going on. If we are looking in the whole genome, it's even worse. I mean, we understand only a few places in the whole genome. So I think what is changing and is so exciting in the last few years is now computational approaches can change that. I mean, can tell you, can inform what are the places in the genome that they are more informative about a particular therapy, a particular mutation, the progression of cancer, the response or non-response to therapy. And this is kind of a project that we've been developing. I mean, I'm just talking here instead of Mohammed. He was in a meeting with White House people even. So, and he asked me to stay here and just tell you something about the work that we are doing. This is work that we are doing from our program for mathematical genomics here. I mean, this is led by Mohammed Al-Qarishi. I'm going to be talking only about the work that is on protein structure, predicting protein structure, but the work now is extended for other places in the genome beyond protein structure. So as you know here, I mean, in the last few years, biology has been traditionally a very descriptive science. So you see something, you describe what is going on, what are the mutations, you do some experiments. I think now what is different is now we have a lot of data, and we have the means also to extract knowledge from the data. And we can go from the description to the prediction. And I think this is what I call the quantitative challenge. To do predictions that they are quantitative predictions about something that is going to happen in the future in this particular patient with the data that we are collecting all around the world. So, I mean, this is leading to very interesting results. The ones that I'm going to be mentioning here is predicting structures. That is how a protein is folding, and this is telling something about the function or the lack of function of a particular protein. And when you introduce mutations, how this function is changing. The same thing here now in understanding the regulation, looking at places in the whole genome, and how these alterations, we can do CRISPR in silico, we can introduce mutations and trying to see what is the effect in silico of these mutations. And this is high throughput. You don't have to go gene by gene, but you can take the whole genome, introduce mutations, and trying to see what's going on. So proteins are the key effectors of cancer. I mean, as we saw in the previous presentation, many of these mutations, they occur in patients. Many of these mutations, we don't know what is the impact of that, but these are kind of the functional machines in the cells. In the last 2 years, there have been these AlphaFold developments, as you probably know, that is trying to understand what is the structure of the protein. And the classical problem is you have a sequence of amino acids here on the left, and then, so taking this sequence of amino acids, trying to predict what is the three-dimensional structure and what is the function of this particular protein. And then this not only, predicting the structure of a protein, but how a protein is interacting with a different protein, how a protein is interacting with DNA or RNA, or how a protein is interacting with the small molecules, some medicines. So this is now moving very fast. Methods are being developed. If you go to the bioarchive, they're not even in papers, but they are changing very rapidly. So protein structure prediction is a competition, CASP, that every year has been trying to predict the structure of proteins. And till 2016, it has not been very good. The predictions, they were not at the same level of an experiment. But in 2018, there was the first AlphaFold, and it was getting to a level that is almost experimental level. And then now it's just basically very, very high accuracy in these things. So what is very interesting is that here there are two effects. One, I think, is in green and blue. One is the real one, and the other one is the prediction. And you can see that they are basically indistinguishable. Doesn't matter what is what, because they are basically the same. So it's very interesting. Many of the proteins, they have this. Most of them. Some of those, they don't have this prediction. It's very interesting also why they don't. It's interesting. But there are key challenges that are appearing here. There are critical limitations. Most of the predictions at the moment, and they are from individual sequences, something very individual sequences, but they are learned by the structure of all the other proteins that are around. So they are proteins that are orphaned, that they don't have a lot of things around. We cannot learn from the rest. But these methods now, they are learning some of the properties of how to fold these proteins and learning something and make these models generalizable so that you can just go beyond that. So some of the proteins, they have multiple conformations. It's not only a unique structure, but they are different of those. And there are some dynamics also. They are quite interesting. These are problems that are open. Protein small molecule complexes, many people working on that. It's still kind of moving, but it's still far from being that. Multimeric complexes, this is moving very fast. There have been very, very good developments in the last few years. The last few months. How to put together different proteins, how they are interacting and constructing complexes. And again, many different things, incorporating, developing de novo proteins with particular functions, or including unnatural amino acids, things that they are not in nature, how you incorporate this information. So this effort is led by Mohamed Al-Quraishi, and then he has been leading here, centered here at Columbia, this process that is called OpenFold. That is something, AlphaFold was developed by DeepMind, that is a company of Google, but this OpenFold is an initiative led here at Columbia by Mohamed, that is an open initiative. So everyone in the world can collaborate and can participate in these things. There are investigators all around the world from many different companies also, that they are putting resources and they are putting the mind to work in these things. It's kind of a big collaborative effort. And then Brent is going to continue here.
So what are we trying to do with this initiative, this kind of use of AI, machine learning, and prediction, big data prediction about protein structures? So we're focused initially on enzymes. So enzymes are basically the proteins that carry out much of the chemistry of cells, and they're also key to many cancers. They become mutated and altered in many cancers and are the targets of various various medicines. So can we predict different conformations, the different shapes of mutated enzymes, mutated kinases, for example, other metabolic enzymes that carry out the reactions of metabolism and might help us diagnose and eventually treat cancer better if we can understand these shapes and how to design small molecules or medicines that can interact with those proteins. So the key is not just to make the predictions, of course, but also to integrate the computational side with the experimental side and accumulate better data that then informs the next generation of predictions. So one of the cases we've been looking at is an enzyme, a protein called glutathione peroxidase 4. It's involved in a reaction that protects cells from damage to their membranes. And it turns out that certain aggressive, drug-resistant, advanced stage cancers become very sensitive and depend on this repair enzyme. It turns out there's actually a patient mutation that occurs in a relatively rare, a small number of kids that we found causes a partial loss of function in this enzyme. So it's not a complete loss of function, but a partial loss of function. And it does that by destabilizing a loop in the protein. And so that loop becomes floppy, and now the enzyme doesn't work the way that it normally should. So what we wanted to do was try to correct this, and we took originally an experimental approach. So we screened over 2 billion chemicals to find some that might interact with the protein, and then to see if any of these could actually correct the single point mutation in this patient-derived mutant protein. And incredibly, it seems like science fiction, we actually found a few that do this, and then we're able to even improve them a little bit further, and they restore that loop, and they activate the enzyme function, and they restore the properties of of cells from patients with this mutation. These are not medicines. There's still a long way to go to get them to the point that they could be tested in people, but nonetheless, it's a proof of concept that you can correct some of these mutations that are found in patients, but it took a long time, and it's still taking a long time, and it's difficult, and it's expensive. So maybe with AI and computation, we can do this faster and better. I mean, in particular, as I mentioned, the same protein becomes a dependency in metastatic cells and drug-resistant cancer cells. They become resistant to many conventional therapies in the course of treatment, but these cancers that make up kind of minimal residual disease and that later recur, many labs have found, including ours, that these aggressive cancers become very sensitive to inhibitors of this enzyme. So if we can design better inhibitors, we can test that hypothesis that we could treat these cancers through this mechanism. So we have a good data set as a starting point, and we're working on using computation to now design better inhibitors than the ones that we've identified. So what's the vision for the long term? In a year, let's say we'll have this platform set up and be able to evaluate OpenFold on experimental data that we're acquiring here and kind of iterate that prediction system. In 5 years, we think we'll be able to have the computational methods in place to rapidly design new therapeutics, not just interaction with proteins, but all the other properties we need to make an effective medicine. And then the dream, the vision, would be in 10 to 20 years, for any protein of interest, it's mutated, it's altered, it's critical in certain cancers, you can just order up a custom medicine the way you can for an antibody or a piece of DNA today. So that's where we hope to go. We'll stop there. Questions?
This is more of a comment, very exciting. I do remember, however, a meeting that was convened about a decade ago where they were discussing, what sorts of drug discovery should be done in an academic environment versus what kind of drug discovery should be done in industry, where, of course, they can marshal incredible resources. And I think the comment Eric Lander made was about right. He stood up and said, we should only do the kind of drug discovery in academia where, if we succeed, it really messes with people's heads. And, and I say that because, of course, AI, the genie's, out of the lamp and is being used intensively in industry. So hopefully that you'll continue to show us new ways to use it that'll mess with people's heads.
Yeah, that's a great point. And I'll say that often it's the thing that also messes with people's heads is when you have a new target, we say it's unvalidated. And, we've actually talked to industry about this target and they say, well, it's kind of interesting, but it's not yet validated in people. So, come back to us when you've proven it and then we'll be happy to collaborate. And so that's another great way we can do that.
I think I can just ask that.
Yeah, I don't know if Raul wants to tackle that.
So I can say something about, transcription factors are going to be complicated, but I think, for example, one of the things that we are seeing, for example, in many of these interaction with different proteins, you can model some of these mutations that there and what are the partners that are there. So sometimes perhaps you cannot target directly the transcription factor, what it's doing, but some of the interacting partners in this interaction. I think now it's feasible with the technology that we have.
Okay, thank you, everyone. We're going to take about 20-minute break until 3:50. You're welcome to go down to the lobby for refreshments and recharge, and then we'll resume back here with the rest of our symposium.
Okay, our next mini session is devoted to our initiative on human tissue immunity and the normal human tissues, and then the aberrations that occur in tumor tissues and the potential for immunotherapy. This is being co-led by Dr. Donna Farber and Dr. Ben Izar, who will present for the initiative. Dr. Izar is the Milstein Assistant Professor of Medicine and also Director of our Human Immune Monitoring Corps. Ben?
Thank you. Okay. Thank you, Anil, for the invitation to present our initiative and for organizing this really amazing meeting today. So before I start, why do we need this initiative? I think we learned a lot of things during the COVID pandemic, and one of them was really a reminder why we need to study tissue. So I joined Columbia towards the end of 2019, and I think we did one successful experiment in early 2020, and we got shut down again. And one way to keep your lab open at the time was actually, participate in COVID research, and that's what we ended up doing, like so many of you here. So Donna Farber's lab and my lab actually at the time got really interested in understanding the immunology that happens in these patients who do poorly with COVID-19. In Donna's lab, she ended up doing profiling, single-cell profiling of BAL. So these are lavages from patients who are intubated, where you can get part of the local microenvironment from the lung. And they compared that to blood. And what was really intriguing is they learned a lot from the BALs that they couldn't have learned from the blood. For instance, they found that certain T-cell populations that are shown here in this green color were not present in blood. So there's no way for us to learn from blood what we need to learn. And importantly, those are the populations that seem to be associated with good outcomes in those patients. And similarly, they looked at the myeloid compartment and they found that the myeloid compartment in the lung was very different from that in the blood. And again, later on, we found out that those are actually the drivers of the overwhelming inflammatory response. And they came up with this really nice model that explains how the lung tissue and blood interacted, and we couldn't have understood the pathophysiology without looking directly in the tissue. At the same time, my lab got really interested working with the pathologists to study the entire lung tissue. So patients who died during the early phase of the pandemic underwent rapid autopsies. And from these cases, we included 19, we profiled the lungs and we compared them to healthy control tissues that were available. And like Donna and many other people around the world were finding, we also found that the predominant population in the lung were actually myeloid cells. And more intriguingly, unlike any other infection or other reasons for ARDS, we found that in particular in COVID, these myeloid cells were producing an inflammatory cytokine called IL-1 beta, which importantly, as we've shown through some of the trajectory analysis of single-cell RNA sequencing, we're actually directly inhibiting the ability of the lung to regenerate from its stem cell, an AT2 cell, towards an AT1 cell. So this was a great reminder that to really understand a disease, you need to look at tissue. But most of immunology actually is not done that way. I would say for most of our knowledge that we have from immunology really derives from studying blood. But if you look at the actual amount of immune cells that are in the blood, they make up only about 2% of all of the immune cells in the body. So it's really a vehicle more than a sort of an end organ where function happens. As you can see, many other organs such as barrier organs, skin, the GI tract, and the lung are actually much higher amounts of immune cells. So this was really a reminder that we need to start looking at tissue and reimagine how we want to study immunology moving forward. This concept that we would study only blood is very odd to a medical oncologist. So I'm a melanoma oncologist, and one of the first questions that you would ask when somebody calls you up and says, well, there's something on the CT scan, what do we do? Well, a tumor is the rumor, tissue is the issue. We need a tissue diagnosis first, right? Before that, we can't do anything. And this concept is ingrained in every oncologist, has served us really well. From tissue, simple staining, we can learn a lot of things. In the example of lung cancer, we can stratify small cell lung cancer from non-small cell lung cancer and lung adenocarcinoma from squamous cell cancer. With the advent of sequencing methods, of course, we now understand that lung adenocarcinoma is a really complicated, heterogeneous group of diseases defined by different driver mutations, and that has led to the development of a variety of oncogene-directed therapies. The advent of immunotherapy has now really opened our eyes to another component of the tumor, which goes well beyond just looking at a mutation or a genetic signature. It's really to be understood as an ecosystem that is composed of a heterogeneous population of cancer cells, but a variety of other cells, and immune cells obviously playing a critical role to responses for immunotherapies, which I'm sure all of you are now well attuned to. To understand these ecosystems, we have to also reimagine how we study them. What technologies do we need? Until a few years ago, what we would do with these really complex structures is literally take them, grind them up, like you would do in a blender, and then study the DNA or the RNA that comes out of it. But obviously what we lose is the granularity that we need to understand the composition, the interactions, and the functions. And in the last years, technical developments now allow us to dissect these tumors at higher granularity. Single cell genomics being at the forefront. And then an emerging field is understanding these tumors at a high resolution in their preserved architectural context. We now know that it's not only important what cell is in a tumor, but also where it's positioned, how it interacts with other cells and with cancer cells, and that really determines the outcome to responses to immunotherapy and other therapies. So my lab has spent actually a lot of time doing what my former mentor would call unglamorous work. And what I mean with that is these methods are really exciting, but it's very difficult to actually apply them in the clinic. It requires a lot of coordination, lots of infrastructure. So one of the things that we realized really early is to make this broadly applicable to a large population, controlled population of cancer patients, we have to be able to work off of routinely clinically sampled materials, such as FFPE tissues or snap frozen material. And to just demonstrate you how empowering that ability is, I'm going to present a case study of a patient who was enrolled to a clinical trial called Keynote 001. I think we're at 700 right now. But this study was actually the first phase 1 study testing a monoclonal antibody, which would later on become known as pembrolizumab. and probably one of the most important development in cancer therapy. So we called up one of our colleagues at UCLA, Tony Ribas, was one of the principal investigators on the study, and for whatever reason, but thankfully, he had actually collected some biopsies of patients before and during therapy and had stored them as snap frozen core biopsies, right, routinely collected materials. So he was also so nice to send us that material so we could apply these methods and see what we could learn. So apart from doing RNA sequencing, also can do all sorts of other things at the same time, such as whole genome sequencing, T-cell receptor sequencing, and spatial transcriptomics. And this is one of the results from this study that was just recently published. When we look at the single-cell transcriptomes from the before treatment, the pre-treatment, and the subsequent on-treatment biopsies, it became clear that these cells change with treatment, and there is a selection. So what I colored here are the cells based on their underlying genomes, and we can also see here over time that the composition of this tumor changes during therapy, where some clones, such as this red one, get completely eliminated, and others expand and take over the tumor. And intriguingly, similar to concepts from the targeted therapy world, these resistant cells were pre-existing in the tumor. When we do spatial transcriptomics on these, we also find that not only is there an evolution of this tumor, but it's also highly spatially defined. So what I'm doing down here is I'm indicating in yellow that clone that was one of the clones that emerged during therapy and was a resistant one. And as you can see, it's exclusively localized on the bottom part of this tumor. And even more intriguingly, that area of the tumor was completely depleted of T cells. And that is probably a function of those tumor cells, but also the reason that this tumor was resistant. So I think in a nutshell, what we're looking at here is actually what one would call a partial response in the clinic. So now, we want to apply these methods broadly, these and other methods broadly, to normal tissues to understand how do cells normally interact with their surroundings, what maintains a homeostatic signal, and then we can apply these concepts to cancer context. But to study human tissues, you need tissue, and that's not a trivial problem. But fortunately, we are actually very blessed with programs that are already existing. So this program, led by Donna Farber, is basically a cooperation with organ procurement programs in New York City and beyond, where patients who are organ donors, in addition to the organs that are being removed for transplantation, Donna's lab actually gets biopsies of a variety of different organs. So that allows her and us to study multiple organs in a completely normal context. On the other hand, and this is a resource that has been led by Dr. Hanina Hipshush, we have collected tens of thousands of frozen biopsies over the last 30 years and more every year. So we are already starting out with an opportunity to redefine certain diseases and certain organs in a variety of contexts. So what do we do with this and how do we bring this together? As you know, some cancers, such as colorectal cancer or melanoma, are defined by a progressive evolution where they start with one mutation, acquire another one, and so on, and ultimately metastasize. So what we would like to do and what we will do in this initiative is understand not only how the immune system interacts in a homeostatic context, but also at any stage of this tumor evolution. So we want to understand where does the immune system fail in preventing these precursor lesions, for example, to transform to full-fledged cancer. So I think what we will do is we will really map across many tissues and cancer types what immunity looks like. But a really dedicated goal of this initiative is also not only to map, but use that knowledge to make therapies. And I'm going to pick one example that is actually actively ongoing. So to Katrina's introduction earlier, if I had to explain this to a cab driver, I would say, imagine, you're driving this car and that is your immune system that is on its way to try and eliminate cancer cells. This part of the initiative would be, how do we have to tinker and modify that car to make it, better or more economical and faster to identify these cancer cells. And there's different ways to do this, and we've heard already some of them. I'm going to use the example of T cells, which are the dominant sort of effectors of every known immunotherapy so far, or the basis for CAR T cell products, for example. So if you imagine that your T cell is a car, you could do a CRISPR knockout screen, right? And that would be the equivalent of that. You take off a tire of a car, it's obviously not going to drive. But what does that really teach us, right? Instead, what we would like to do, and what we are doing in collaboration with Alberto, is base editor screens. So we want to take every piece of that car and fine-tune it by introducing, in an unbiased fashion, thousands of mutations or variants in key genes or proteins of T cells, and understand whether synthetic variants exist that might be better than the endogenously existing protein. And we do this not completely uninformed. There is tons of population genetic data. There are many, many syndromes, germline mutations that are known to cause either autoimmunity or immunodeficiency. So we have something, we have controls for what we're doing, and also informed by the work of Donna and others and the data that we will generate here. We perturb hundreds of genes and ask, how does this affect a variety of hallmarks of T cell activity? For example, its ability to proliferate, the production of cytokines such as interferon gamma or TNF, or its ability to maintain a progenitor state, which is really important for the response to immunotherapy. Using artificial intelligence tools, what we will do is we will take the results of these connections between mutation or variant and phenotype and try to identify those that would make the most ideal T cell, if you will. And that can be either one variant or it can be a combination of different mutations. And what we will do with these is we will introduce them in a more selective manner in different cell products, such as T cells or CAR T cells, and then test in vitro and in vivo whether we actually are able to improve the activity against cancer cells, its ability, the ability of these cells to maintain and live longer in the mouse, and so on. And ultimately, we believe that this will be a relatively plausible way of rethinking cell therapies also for patients. And one thing that we really interested in is understanding how can we make these cells enter certain tissues. One of the biggest problems of cell therapies, no matter which one you would take, is they frequently don't go where they need to be, and when that happens, it can cause side effects. And so from these atlases that we have started generating, what we would like to do is decode, if you will, the combination of transcription factors or other signaling molecules that determine which tissues these enter. And so we can equip these cells with a zip code and a GPS and tell them where to go in order to make these more efficient and hopefully also reduce toxicity. So I think there's a lot of interactions with the initiatives that we heard earlier. One thing I can imagine is, once we have collected all this data connecting the variants with the phenotypes, we could start predicting, how does this one mutation change the folding and perhaps also the function of a particular cell context. So there are other things that we are aiming to achieve, but I just picked a couple of examples. And of course, I want to thank people in my lab, and Donna is not here, unfortunately, but here are the members of her lab and all the collaborators here and internationally. Thank you for your attention.
Does anyone have a question for Dr. Izar?
Yeah, so the question is, what differences would you expect of a, say, T cell between one tissue type or another? There are actually enormous differences, and that we already started, seeing, for example, a T cell that homes in the gut, for instance, and decides to stay there, programs very differently from a T cell that continuously recirculates to survey a different organ. So there's already actually a lot of prior knowledge from Donna's work and other people's work on determining what what determines tissue-specific T cell residency, for example. So these cells enter the tissue and decide to never leave. They look different in the gut and in the skin and the lung and so on. Good.
Okay, so our last mini session before our keynote talk is devoted to drug discovery. So this is coaxing leads and targets in the preclinical domain and possibly into the clinical domain. And this is an area of much time, energy, and investment internally for our faculty. And this program is being led by Dr. Tanista Reyes, Irving Professor, as well as Associate Director of Translational Research and Director of this program. Tanista?
All right, well, thank you so much for having me here. It's a real pleasure to be part of Columbia because I'm new here as of a year ago. And I've been working over the last year with Dr. Rustige and Emer Smith to build this program. So I do want to start with sort of expressing my gratitude for the privilege of being in an academic institution like Columbia. Academia has traditionally been committed to the goals of teaching and creating new knowledge. And in this commitment, it is not an overstatement to say that it has really revolutionized society. So it's where many of the greatest ideas are conceived and many of the most important breakthroughs in medicine occur, as you'll probably hear right after me. It's fair to say that I think academia has contributed to this world an extraordinary amount of new and important information. And so with this in mind, I did a PubMed search last night for papers mentioning the word cancer over the last century. And so this shows you one way to capture a century's worth of discovery in this field. And it said to me that I have 50 million pages to read about cancer research from the last many years. So even if I don't manage to read all that, I want to say that it's a really remarkable feat. And one consequence of all this effort is that we really understand the human body and human disease much better than we used to. But while that in and of itself is a worthy accomplishment, one question that haunts me and probably many of you is how do we make sure that all of this knowledge has the opportunity to reach the people who are waiting for cures and looking for a new option that could change the trajectory of their disease so that they too could be a survivor. So this is another way to look at this question. A university's research budget, somewhere in the $1 to $2 billion per year range, and this is almost completely devoted to discovery research. And this really forms a foundation, I would say, of a lot of drugs that are developed, vaccines that we use, but this part of it is the purview of pharma. And a pharma's operating budget is about $60 billion per year, one of them, but they almost completely use these funds for late-stage development. So this is a compound that's already been made, an antibody that already works, or a drug that has already cleared trials. So really what this does is leave us here where you can see the resources on this axis here, and you can see academia coming in with billions to support research, discovery, new knowledge, and industry here really focusing on late-stage drug development and pharma buying biotech, et cetera. And what that really leaves behind is this translational space where the resources to really get this information and this knowledge over into the hands of industry, these resources are vanishing. So what this does is really leave many scientific discoveries that have the potential to impact care, leaves them behind on the lab bench, and these may never have a chance to really go beyond the lab. So to me and to many of you, this is a lost opportunity. So what do we do about this? So this is what I've been working on with Dr. Rusky over the last year. And the hope is that building a drug discovery program here will bridge this gap and bring critical resources and support to the researchers working to bring new cancer drugs to the clinic. And the goal is really to develop an incubator program that can mature early stage projects within academia before seeking external support. It'll build a stronger foundation for these projects to increase their likelihood of success for external funding and support, and increase their valuation at exit so that that can now be reinvested back into academic translational research. What we hope to do is really provide end-to-end support from the end of a discovery all the way to the beginning of a trial at various stages, starting from a validated target that needs a screen, a chemical matter that needs to be optimized, all the way to preclinical testing of a compound that is ready to go into the clinic. We also want to support a broad range of programs serving the needs of the faculty, and this can come in diverse modalities like small molecules, biologics, cell therapy, computational biology, artificial intelligence, diagnostics and devices. So the way we have structured this is heavily externally dependent, a strong governance structure coupled with strong funding that allows you to do some significant work to position it for external funding and support, advising and counsel from seasoned drug developers who are brought in from biotech and pharma, research resources that are coordinated, integration with the clinical trials group so that there is that information on pathways and trajectory to the clinic, and then finally working with Columbia Technology Ventures for IP management and business development. The outcomes that we hope for is to really create a high-impact innovation ecosystem in the Cancer Center here so that it accelerates faculty-driven startups, new partnerships with pharma, biotech, launching new clinical trials, and has the opportunity to help the person that is really waiting for all of our discoveries to lead to the clinic. So we hope to build this bridge so that we can finally get the discoveries that we make daily over into the hands of Columbia doctors. So I'll just say that we had an extraordinary year with an incredible number of exceptional applications, really exciting work that really needed the support. And I'll just go through this briefly to say that there are 4 funded projects from this year. One is Dr. Acharya leading a group to target cancer cachexia, Dr. Orange developing strategies to improve cell therapy, Dr. Shen, who's developing a small molecule against prostate cancer, and Dr. Peter Connell, who's leading a team to develop a device which will deliver a drug for GBM, therapy-resistant cells. So I'm going to hand it over to Peter and Jeff, and they will take over and highlight this project for you.
Okay, thank you. It's a pleasure to be here representing this really top-notch team of investigators who are working with the Cancer Discovery Program. And we're going to talk about what we're doing here with glioblastoma. Now, glioblastoma, you can see here's a picture of a typical patient. She's 63 years old, comes in through the emergency room with a seizure, and this is her scan. And any neuro-oncologist can instantly look at that scan and realize this is glioblastoma, and it's the most common malignant brain tumor, same tumor that Ted Kennedy had, same tumor that Joe Biden's son, Beau Biden, had. And what this patient is going to, doesn't know yet, but she's soon going to learn, is that this is one of the most deadly human cancers known, that the standard treatment is maximal surgical resection, followed by radiation, and then chemotherapy with a drug called Temodar. And with that treatment, the average survival is in the range of 12 to 15 months. And these tumors, when they grow back, and they grow back 100% of the time, the average survival is on the order of a few months. And when they grow back, the only options available are experimental protocols. So looking at this difficult tumor, why can't we simply remove them? Well, if we look at this model of the brain and we put a tumor there, and if you remove the tumor, you can remove it as completely as possible, but there's still going to be some tumor cells there. And those tumor cells are invading the brain, and they are what's responsible for this tumor growing back. So you need a strategy to attack those tumor cells. So you've already given radiation, you've already done maximal tumor resection, you've already given the one chemotherapy drug that works. Why aren't there other good chemotherapies? Well, the issue is that we have lots of good drugs that effectively kill tumor cells, either in an animal model or in tissue culture. But the problem is not that these drugs aren't effective. The problem is a drug delivery problem. We can't get them into the brain at high enough levels to be effective. Standard chemotherapy is systemic delivery, is either intravenous or taking a pill. That drug's got to go through your entire body, and only a small amount of it gets to the brain. When it gets to the brain, it hits the blood-brain barrier, which is specialized blood vessels in the brain that nature designed to keep these drugs out. So we got good drugs, we can't get them into the brain. And if we start with that problem, what other options do we have? Are there alternative drug treatments, drug delivery methods? And we can look at some features of glioblastoma that are very unique. One of them is that if you remove a glioblastoma, 90% of the time it's going to grow back at the same spot that you took it out from. And the other thing is, unlike almost every other human cancer, these tumors rarely metastasize. So you're dealing with a tumor that's growing back locally. And what if you had a strategy to deliver drugs locally? If you look at that MRI scan, you can see the tumor outlined there, and then you see this white high T2 signal, which we know is brain edema. That's a response to the tumor. And essentially, that's just fluid in the interstitial space, fluid between the cells in the brain. And that volume is the approximate volume where the tumor cells are invaded. So if you can get your drug at adequate levels into that volume, you're going to make an impact on the clinical effects of the clinical progress of this disease. And so with that in mind, we started working on a concept called convection-enhanced delivery. And this is a way of delivering drugs directly into the brain, completely bypassing the systemic circulation. And the way it works is the brain is actually like a sponge at a lot of level. You look at it microscopically, you see brain cells, but there's fluid around all of the cells, and there's actually a microcirculation around them. If you take a simple catheter and surgically implant it in the brain, and then connect it to a microinfusion pump. So that pump slowly infuses your drug at the very slow rate, several drops an hour, 200 microliters an hour. If you infuse it too quickly, it just squirts up around the catheter, it doesn't penetrate. But if you do a very slow infusion, what happens is at the catheter tip, you set up a pressure gradient that's now pushing your drug through the interstitial space. And you can achieve very high concentrations of drugs for several centimeters. You can infuse a volume of 12 centimeters or more, which is almost half the hemisphere of the brain, more than half the hemisphere of the brain. And so we looked at a number of drugs. We screened lots of drugs in our lab with animal models, tissue culture, and tried to find what's the best drug to start our clinical trial with this. And we looked at a lot of drugs, and almost all of them worked. Almost any drug is going to be more effective if you can put it right in the brain rather than with systemic delivery. And we found a drug called topotecan, which is a topoisomerase inhibitor. It's a drug that's routinely used for lung cancer, was the most effective in our preclinical studies. Not only was it effective at killing the tumor cells and extending survival, but it was relatively non-toxic to the brain. So we did a phase 1 trial with this. And here you see one of our patients. You can see coming out of her head, she's got a little bandage there, but there's a catheter that's implanted into her brain right next to her tumor. It's connected to tubing that is then connected to a microinfusion pump on that pole as she walks around the halls. This is in the Irving Center for Translational Research. And she's getting the drug infused constantly over the course of 4 days. At the end of 4 days, we simply pull the catheter out. And here you can see the results. This is one patient. This is a Princeton physics professor who had a recurrent glioblastoma. We treated it. You can see 12 months later, you can barely see his tumor. That patient should have had an average survival of about 3 or 4 months at the time we treated him. He went on, he ultimately died 18 months later. But the point being that we were able to establish a maximally tolerated dose for this drug, topotecan, and it was extremely well tolerated. So there's a problem, though, with this system. And the problem is, because we're relying on an external pump, we have to worry about infection. This catheter is coming out of the brain. You got maybe a week before it's going to get infected. So at the end of the week, you have to pull it out. That means you're limited to a single treatment for only 4 to 7 days. And with everything we know about cancer, most cancer drugs, to be effective, they have to be given over multiple doses over as long a period of time as possible. So to address that problem, we came up with another strategy, and that was to use an implanted pump that gets implanted in the abdomen, connected to the tubing, tunneled under the skin, and then connected to the catheter. So everything is under the skin, and the pump is sitting in the abdomen. It's about the size of a hockey puck. And this pump has a wireless technology, so you can turn it on and off. And it's also got a little diaphragm in it, so it's sitting in your abdomen, and you can feel for that diaphragm. You can take a simple needle and syringe, and you can percutaneously access the pump to refill it with drug as often as you need to. And so with this concept, we did some animal studies to get FDA approval for our feasibility study, and we did a clinical trial with 5 patients. Here you can see the MRI. This is a typical patient. You see the second scan there. What we did was, in addition to infusing the topotecan, we infused gadolinium. So that way we could do an MRI scan. We could see where the drug is going. And this is the gadolinium, and it shows the volume of distribution. But in fact, when we measure drug levels, the drug levels go much further beyond what you're seeing on the MRI scan. So it's a rough estimate, but it significantly underestimates the volume. And here you can see our real estate executive during treatment selling a house there online. And so this was a pilot study. We only had 5 patients. First time this has ever been done. And we limited it to just 30 days because we just wanted this proof of principle. At the end of 30 days, they came back in and we took their tumor out. But this then presented a very unique opportunity for us, this unique clinical trial. Because we had to go to surgery to put in the pump and catheter, when we did that, we did multiple MRI-guided stereotactic biopsies of the tumor and the surrounding brain. So we now had tissue in the brain and in the tumor before treatment. At the end of the month, after they had gotten their treatments, they came back to the operating room. We took out the pump and catheter. We removed the tumor, and we took an additional set of biopsies. So now we have this unprecedented resource. We have tissue before treatment. We have tissue after treatment. I don't know of any brain tumor trial that has that kind of resource. And with that, we're able to utilize our great team here to do a tissue analysis. This is a very brief summary of it, but we're able to do simple immunohistochemistry staining to look at different markers. We're able to isolate RNA, do RNA sequencing. We're able to use MALDI to measure the actual drug levels so we can see exactly how much drug was getting in there. We could do gene set variation analysis so we could see the effects of particular tumor subtypes, different cells. And overall, what we found is that neurons were unchanged, meaning the neurons were unaffected. So normal brain cells were not affected by the treatment. We dramatically reduced the number of tumor cells, proliferating tumor cells. We nearly eliminated them. And we identified a very interesting group of quiescent tumor cells. They're of a specific subtype that were not very aggressive, not proliferative, but they likely are responsible for why the tumors grow back after this kind of treatment. So with all of this system in place, it gave us a unique ability to interface with the drug discovery team on some unique challenges, because now we have kind of solved we think, the drug delivery system, we can use multiple drugs. We can address the heterogeneity of gliomas by giving multiple drugs. We can give drugs over, here we did a month, but we can do 6 months, we can do a year, we can do forever, as long as we can continue to have our system in place to deliver drugs. And we also have this unique opportunity to analyze tissue to see at a very granular level what our drugs are doing to the tumor and the microenvironment. So with that, I'm going to introduce the leader of our team, Peter Knoll, who's going to discuss how things have progressed now with the drug discovery team and meeting these challenges.
Thank you, Jeff. So I'm going to bring it back around to the drug discovery program, and I want to introduce the team of principal investigators that we're all working together. As Jeff just explained, his clinical trial has really addressed some of the major challenges to treating this disease, but in the same time, it's presented us with other major challenges that we have to face. And the drug discovery grant that we got is to help us address some of these key challenges, and each of the principal investigators are bringing some expertise to that. Peter Sims, who's shown next to Jeff there, is a systems biologist and an expert in single-cell sequencing. He's been collaborating with us for many years to try to understand the cellular composition of brain tumors. And he, in collaboration with us and Osama Aldalama, who's another neuropathologist like I am, have started to use tissue samples to test out the effects of different drugs on different tumor cell populations. And one very novel system that we've developed is to take surgical samples that we get from Jeff and other neurosurgeons, bring them into the lab, generate acute slices, and then treat them ex vivo in a tissue dish with different drugs, and then do single-cell sequencing and other types of analyses to identify the effects of these drugs on the different populations. And what we've discovered from that is that, as Jeff said from his clinical trial, these proliferating subpopulations can be targeted by topotecan and other drugs that kill proliferating cells. But there's populations of quiescent tumor cells that are found in all of the tumors that we've looked at that are resistant to these standard forms of chemotherapy. And through years of research at studying these particular population, we've identified that they have a metabolic vulnerability that makes them sensitive to drugs that induce a certain type of cell death called ferroptosis. And this is where Brent Stockwell comes in. If you guys were lucky enough to see his talk earlier, he actually was showing work he had done on a metabolic enzyme called GPX4, which is really important for protecting cells against ferroptosis. And not only did he do these landmark research to identify ferroptosis as a form of cell death, but he's also generated a whole host of drugs that can affect these molecules, inhibit GPX4, and induce ferroptosis. And so we've been using the drugs that Brent has developed to see if we can effectively target this non-proliferating quiescent population. And we've tested a whole bunch of drugs. The one drug that is the single most effective drug so far is this drug that was developed by Brent called RSL3. I think he might be holding a model of RSL3 in that picture. And he's generated a host of new derivatives of RSL3, and what the drug discovery program is funding us to do is to take those drugs and put them through these same preclinical mouse studies and the tissue-based analysis to see if they can also target more effectively the quiescent population, with the ambitious goal at the end of this to bring this back in the clinical trial, the same kind of clinical trial that Jeff has originally done with the topotecan we're going to try with these new drugs. In order to do that, we're going to face some of this valley of death challenge that Dr. Rea presented to us, where we have to try to advance something from the lab into the clinic. And One of the things that the Drug Discovery Program has done is they've teamed us up with Bruce Conway, who is a researcher from Rockefeller University with real-life experience of getting drugs from the lab into the clinic. Already, he's been really helpful in helping us plan our experiments, and so even though we're at a really early stage, this Drug Discovery Program is paying off big. And that is a picture of me over to the left, actually making this slide. So I wanted to prove that we're all doing our part in the program, okay? And I want to end by saying that these are the 6 principal investigators in this drug discovery program for this project. But what's not shown here is a real host of a number of researchers, outstanding researchers in all of our labs that are working together to make these discoveries and help us advance this to the next level. Thank you.
Any questions for Drs. Bruce and Knoll or Dr. Rea?
Yeah, so the question was, how did we end up with ferroptosis as a target? And I would attribute that to 2 things. There's a literature, existing literature, that ferroptosis is targeting drug-resistant cells that Brent alluded to. But also, there was a neurosurgery resident named Matej Banu who was working in the lab studying these drug-resistant cells in glioma. And he reached out and went to Brent's lab and set up a collaboration with the idea we're directly going to test the ability for ferroptosis-inducing drugs to target that population. So I would say Matej made that initial, it had that initial inspiration to test it. We then tested it, and that led to, as I said, years of research to try to understand the metabolic vulnerabilities of these quiescent cells that actually make them sensitive to ferroptosis.
I think these mini sessions have been truly invigorating, and they're an appropriate prelude to our keynote lecture. And I'll give some words about our distinguished speaker, Dr. William or Bill Kalin, born in New York City, and then fast forward, did his undergraduate degree at Duke University, majoring in mathematics and chemistry, stayed there for his medical degree. Fast forward, he's now on the Duke University Board of Trustees. After completing his medical school, he did his internship and residency and chief residency at Johns Hopkins, and then went to Dana-Farber Cancer Institute to do his initial clinical and research fellowship, and he's stayed on since. His postdoctoral fellowship was a dive into the function of the retinoblastoma protein, tumor suppressor protein, and family members under the late, great Dr. Livingston. And then that set up a time in 1992 when Dr. Kalin established his own lab and subsequently rose to the rank of Sidney Farber Professor of Medicine at Dana-Farber and Harvard Medical School and investigator in HHMI. Apart from studying the RB protein family, Dr. Kalin's also studied the P53 tumor suppressor protein and its orthologs, and in particular another tumor suppressor protein, VHL, and its interrelationship with the HIF proteins and downstream effectors that's become the basis for translational therapeutics, exciting clinical trials, and standard of care in clear cell renal carcinoma and applications in anemia, kidney failure, stroke, and myocardial infarction, especially exploiting knowledge that he has elucidated in oxygen biology and applications to cancer and non-cancer states. So that body of work has led to a huge host of honors and awards that I'll try to encapsulate. One is awards through foundations, professional societies, the Lasker Award, the Nobel Prize, and most importantly, a plaque from us today from the Cancer Center. And that plaque comes from the heart and soul of the Cancer Center. So it's really our collective honor to welcome Dr. William Kalin for our keynote lecture. Thank you.
Is there a laser pointer? Okay, okay, and there's a laser? Just use that. Okay, good. Okay, well, but people can probably see my arrow here too. That's good. Okay, yeah, we're good. Title slide. No, that is great. Well, thank you very much, Anil, for that very nice introduction. As was mentioned, I was born in New York. I was born in Jamaica Hospital in Queens, and then I grew up in Nassau County, and then Fairfield County. Turns out my father was first generation college, and he was a lawyer in New York, and his father was a manual laborer who used to lay reinforcing steel, including, for example, for the Verrazano Narrows Bridge. So when I was a young boy, I would proudly tell my friends that my grandfather built the Verrazano Narrows Bridge, which was technically a true statement. So here's my disclosure slide. Now I'm mindful we're running a little bit late, and sort of my good news, bad news is I'm capable of speaking New York fast, and this audience knows what I'm talking about. But I try to keep my slides relatively simple. So frankly, even if you weren't listening to me, you'd probably get the gist of what I was talking about anyway. So what I thought I would do is, for the benefit of the young people, and because you have to dance with the one who brought you, I'm going to spend about 10 or 15 minutes talking about the work that led to the Nobel Prize, and then I'm going to move on to 4 unpublished stories. So some of my colleagues will be forgiven if they check their emails for the next 10 or 15 minutes. So here are the people who've done the work on von Hippel-Lindau disease over the years in my laboratory, and here are some of our collaborators who are responsible for some of the unpublished work I'm going to share with you. As was mentioned, I was a chief resident when I was younger at Johns Hopkins and thought I was going to be a clinical doctor, but then I had the very good fortune of meeting the great David Livingston, who was my mentor at the Dana-Farber, and it was really David who taught me how to become a scientist. And you know, so much of becoming a scientist is really taught through apprenticeship, and David was a master. So David, I really owe my career to him. So shortly after I finished my work in David's lab, I read a paper about the isolation of the so-called von Hippel-Lindau, or VHL, tumor suppressor gene, and having been a chief resident, I knew a lot about diseases like von Hippel-Lindau disease, and I decided for a number of reasons that this would be a great gene to study. So here are some families with von Hippel-Lindau disease who have been followed at the National Cancer Institute over time. The filled circles and squares are affected individuals who have manifest one or more tumor types. The classics are kidney cancer, and in particular clear cell renal cell carcinoma, which is by far the most common form of kidney cancer. Blood vessel tumors called hemangioblastomas, and neural crest tumors called paragangliomas, which when they arise in the adrenal gland are called pheochromocytomas. So this disease affects about 1 in 35,000 people. It was first described in the medical literature about 100 years ago, but in hindsight, some of these families have had this disease for several centuries. So just, again, to make sure everyone's on the same page here, even though clinically this looks like an autosomal dominant, at the molecular level, it's caused by an autosomal recessive mutation. So individuals with von Hippel-Lindau disease have inherited a defective copy of the VHL gene from mom or dad. In this schematic, it's the maternal copy. But initially, they're okay because they have the remaining wild-type copy from the other parent. But unfortunately, if you're born with a mutated VHL gene, you have about a 90% chance that a susceptible cell in your body, such as in the kidney or the brain or the eye, will lose the remaining copy and go on to form a tumor. Now, as you would predict from the knowledge that germline VHL mutations predispose to, for example, kidney cancer, if you now look at non-hereditary kidney cancers, again of the clear cell type at least, you again see that loss or inactivation of the VHL gene is a common event and is again the initiating or so-called gatekeeper event. And we know that in part from the work of Charlie Swanton and co-workers who have done spatially distinct biopsies of kidney tumors and then have done deep sequencing and used mutant allele frequencies to infer the evolutionary histories of those tumors. And almost invariably, they see that the inactivation of the VHL gene is the initiating event. And then later on, you see these stereotypical cooperating events, many of which occur in a subclonal or branching fashion. And in this setting, the inactivation of the maternal and the paternal gene are the results of somatic mutations in contrast to VHL disease, where the first hit has occurred in the germline, which is to say this is a very well-behaved so-called Knudsen 2-hit tumor suppressor gene. Now, I knew from my clinical training that the tumors linked to mutations in the VHL gene are very angiogenic, and that's because they frequently overproduce vascular endothelial growth factor, and on occasion, these tumors also cause patients to make too many red blood cells, and that's because these tumors sometimes ectopically produce erythropoietin. And what VEGF and erythropoietin have in common is they're normally induced when cells or tissues are not getting enough oxygen. Now, VEGF and EPO are examples of so-called hypoxia-inducible genes that are normally actively transcribed when cells aren't getting enough oxygen. And we knew from the work of multiple laboratories, including my fellow laureates, that these hypoxia-inducible genes are often under the control of a heterodimeric transcription factor called hypoxia-inducible factor, or HIF, which consists of an unstable alpha subunit, which is normally degraded when oxygen is available, hence the name HIF, and a stable beta subunit, which often goes by the alternative name of ARNT. And over time, our lab and others showed that the VHL protein product is part of a ubiquitin ligase complex that in the presence of oxygen binds directly to the HIF alpha subunits and targets them for proteasomal degradation, whereas when oxygen levels are low or the VHL protein has been mutated, now HIF alpha can accumulate, dimerize with its partner protein, HIF beta or ARNT, and activate genes such as VEGF. So that was very satisfying. Now we could understand why these tumors would have high levels of VEGF and on occasion EPO. But it still begged the question, how does the VHL protein know, if you will, excuse me, whether oxygen is available and hence whether it should target HIF alpha for destruction? And in work that we did and Peter Ratcliffe did in parallel, we discovered that in the presence of oxygen, one of two prolyl residues gets hydroxylated on HIF alpha, and that then generates a high affinity VHL binding site. This oxygen atom of the hydroxyl group, not surprisingly, is derived from ambient oxygen. You can show that in tracer studies. Importantly, the enzymes that do the work here, which are variably called the EGLN or PHD prolyl hydroxylases, have relatively low oxygen affinities, and hence they're very sensitive to changes in oxygen availability over a physiologically relevant range. I will contrast that, for example, with the collagen prolyl hydroxylases, which have extremely high oxygen affinities. You'd have to be virtually anoxic before the collagen prolyl hydroxylases would become inactive. Parenthetically, these enzymes also require reduced iron, which is why adding iron chelators to cells in culture will mimic a hypoxic response. And they require a cofactor from the Krebs cycle called 2-oxyglutarate, or alternatively alpha-ketoglutarate, that gets decarboxylated to succinate during the hydroxylation reaction. And as Anil mentioned, there are already a number of companies that are developing or have developed drugs that act competitively with respect to 2-oxyglutarate, inhibit these enzymes, and thereby simulate a hypoxic type of response. And these drugs are now being used to treat anemia around the world and look promising in preclinical models of heart attack or stroke where there's a problem with oxygen delivery. Now, there are three members of this family, EGLN1, EGLN2, and EGLN3, and they live in a larger superfamily of so-called 2-oxyglutarate dependent dioxygenases. So here are the enzymes that modify HIF. Here are the collagen prolyl hydroxylases you might have studied in college biochemistry. But there are a number of other interesting enzymes in this family, and it turns out they're all sensitive to changes in metabolism, and they all potentially can be drugged. So here are the so-called Jumanji-C histone demethylases, which are very important in terms of epigenetic control. Here are the TET enzymes that are mutated in a subset of acute leukemias, and there's some other less studied enzymes here as well. Now, several years ago, we wanted to know whether, for example, some of these histone demethylases might be like the HIF-modifying enzymes and be sensitive to changes in oxygen, or would they all instead be more like the collagen prolyl hydroxylases and be relatively insensitive to changes in oxygen because of their high oxygen affinities. And it turns out you can find examples of both. So, for example, it turns out KDM6A, which also goes by the name of UTX, a professional tumor suppressor in its own right, is exquisitely sensitive to changes in oxygen and directly links oxygen availability to changes in histone methylation and thereby to gene expression programs. Now, returning to this slide I showed you earlier, it was very clear that it was plausible that excessive HIF activity was responsible for the tumors caused by VHL loss, but someone actually had to do the experiments to see if this was really causal or not. And so many years ago, our lab showed that if you restore the function of the VHL protein in a VHL defective renal carcinoma cell line, they lose the ability to form tumors. And so Keiichi Kondo in the lab took these cells and introduced a form of HIF alpha, and in particular HIF2 alpha, that couldn't be recognized by the VHL protein because of a proline to alanine substitution. And these cells regained the ability to form tumors. And in a complementary set of experiments, he eliminated HIF2 alpha using short hairpin RNA technology, and that was sufficient to prevent them from forming tumors. And not shown here is, first of all, when we did the same experiments with the better studied HIF1 alpha, if anything, to our surprise, the effect was quite the opposite. And in fact, at least in kidney cancer, and it may be peculiar to kidney cancer, HIF1 actually seems to be a suppressor of tumor growth. And perhaps for that reason, many human kidney cancers no longer express HIF1 and exclusively express HIF2. Also not shown here are the controls that you really want to think about if you're going to do these types of experiments. And one of the many things I learned from David Livingston is the experiment's only as good as the controls. So for the young people, here's your required reading, where I've tried to capture in 8 pages every mistake, artifact, and the like that I've seen over the past 25 years in experiments of this type. And you may know that our colleagues in industry tell us that 50 to 90% of the time when they go to read a target validation paper from academia, they either can't reproduce it or it's only true under an extremely narrow set of conditions, which is to say it's not robust. So if you're going to be in the business of looking for targets and validating targets in preclinical models, I think it's really important that you do some of these controls. So what could we do about this therapeutically? Well, we knew by the 90s that VEGF was a major angiogenic factor, and there were companies making inhibitors of VEGF, and we argued that if these VEGF inhibitors were going to work in any solid tumor, they should work in kidney cancer because of this intimate link between VHL loss, HIF activation, and consequently upregulation of VEGF. So predictably, kidney cancers are using VEGF as the major angiogenic growth factor. And I'm happy to report we're now up to 8 VEGF inhibitors that are approved for the treatment of kidney cancer. And some patients do well on these drugs for years. That's the good news. But the bad news is not every patient with kidney cancer will respond to these drugs. And even those that do will usually progress within months to a few years. So how can we do better? Well, just based on first principles, you might say, well, better than targeting any one HIF responsive gene, maybe you should target HIF itself. And based on what I just told you, you should be targeting HIF2. But the conventional wisdom, and students, beware of conventional wisdom. The conventional wisdom was that HIF as a DNA binding transcription factor was not druggable. I heard that for about 20 years. However, 2 very talented scientists, Rick Bruick and Kevin Gardner, who were then at UT Southwestern, identified a potentially druggable pocket in the so-called PAS-B domain of HIF2 alpha, which is what I'm showing you here. And they did high throughput screens at UT Southwestern and identified chemical matter that could bind to this pocket and in so doing induce an allosteric change in HIF2 alpha such that it would no longer bind to ARNT and hence no longer bind to DNA. Now my drug hunter friends told me that these chemicals were publication grade but not pharmaceutical grade. They had many, many blemishes and warts that a real chemist, and I see we have some real chemists here, would say this is not going anywhere. This is not a drug. So fortunately, UT Southwestern was smart enough to out-license their chemicals to a biotech company called Peloton Therapeutics that was later acquired by Merck, and I should declare I have a financial conflict of interest in these compounds. And the medicinal chemist at Peloton improved the drug-like properties of these chemicals substantially. They improved their potency, their specificity, bioavailability, et cetera, et cetera. So we were fortunate. I was consulting for this company at this time, so they provided us with a tool compound called PT2399 that was 1 or 2 atoms different from what was then the lead compound. And our lab and the lab of my former postdoc, Jim Brugarolas, showed that this tool compound did everything you would hope for in preclinical models of kidney cancer. It lowered HIF2 dependent transcription, decreased growth in soft agar, decreased orthotopic tumor growth, et cetera, et cetera, et cetera. So you want to do eureka, high fives, but again, it's all a matter of the control. So here's the soft agar assay that Chin Cho in my lab did. So these are soft agar colonies formed by a VHL mutant renal carcinoma cell line. She treats with 0.2 or 2 micromolar of the HIF2 inhibitor, and the colonies almost go away, and so you go, terrific, that's great. But I also point out this is the kind of experiment that gives cancer pharmacology a bad name. because I could do this with Clorox bleach. I could do this with formalin. How do you know this is really on target and interesting? Maybe it's true and unrelated. Maybe this chemical inhibits HIF2, but it does a lot of other terrible noxious things. Or maybe it's because it's doing the noxious things that HIF2 activity is going down. That would be even the worse. Right? And I will tell you, at 10 to 20 micromolar, this compound inhibits cancer cells that don't even express HIF2. So by definition, that's off target. So how would you know this is on target? Well, the way you would like to do this is with the so-called rescue experiment. And fortunately, Bruick and Gardner had already identified a point mutation of the HIF2 alpha pocket that would prevent the drug from entering the pocket, but would otherwise leave HIF2 alpha intact. And so using CRISPR, what Cho did was she actually generated isogenic kidney cancer cells that either had wild type HIF2 alpha or the HIF2 alpha with the drug resistant allele. And now you can see that these cells are resistant to the drug. Not shown here is it also rescued the ability of these cells to form tumors in nude mice. Now, eventually, an improved version of this compound called belzutifan went into clinical testing for patients with advanced kidney cancer who had failed one or more VEGF inhibitors and had also frequently failed one or more so-called immune checkpoint inhibitors. And so these are so-called swimmer's plots. Each horizontal bar is a patient on the trial and how long they were on therapy at the time of this analysis. For orientation, here's 1 year on therapy. The black arrow patients were still doing well at the time of this analysis, and the yellow star patients had a RECIST partial response. So despite this being a very heavily pretreated population, it looked like maybe some of the patients were deriving a benefit, and based on these data, the drug went into phase 3 testing, which I'll return to later. Okay, I told you I could talk New York fast. So now we're into now we're going to get to some unpublished data. So the first story I'm going to tell you about is work of Nitin Shiroli. So Nitin wanted to ask the following question. With respect to that anti-proliferative effect of the HIF2 inhibitor, are all HIF2 target genes created equally? Now, HIF2 regulates hundreds of genes, and many of them you might intuit would play some role in tumorigenesis. But for simplicity, let's imagine there were 4 genes, A, B, C, and D. So you come in with your HIF2 inhibitor, and now you downregulate the HIF2 responsive genes. And so what he wanted to know was if I artificially restored the expression of any of these genes using CRISPR-A technology, would that at least partially overcome the anti-proliferative effects of the HIF2 inhibitor? So CRISPR has been one of the themes today, and it's going to continue to be a theme in my talk. This is another variation called CRISPR-A or CRISPR activation technology. And so the idea was, I'll go along and I'll activate different HIF2 target genes and see if any of them confer a fitness advantage in the face of the HIF2 inhibitor. So we're using a technology that was developed by John Dench and his team at the Broad Institute. I'm sorry it's so complicated and baroque, but this is one of the versions that works very well. So you have a nuclease dead Cas9 that's expressed as a fusion with a transactivation domain VP64. And then you have this highly complicated re-engineered sgRNA that, in addition to binding to the target gene, is going to recruit some additional transactivation domains for good measure. So now the experiment was as follows. So Nitin took a cell line, a renal carcinoma cell line that was very sensitive to the HIF2 inhibitor. He introduces a genome-wide CRISPR-A library into these cells, having previously stably expressed the right Cas9 variant. The cells were treated with DMSO, or the HIF2 inhibitor, and then at various time points thereafter, he monitored guide abundance simply using next-generation sequencing. So here's one way of depicting the results. So this is a so-called volcano plot. So on the right here are genes that, when are activated, cause at least partial resistance to the HIF2 inhibitor. And over here are genes that, when activated, actually make you even more sensitive to the HIF2 inhibitor. So then what Nitin did was simply bioinformatically look over here for known HIF2 target genes in renal cell carcinoma, and the top scoring gene was cyclin D1, which we've known for years is a direct target of HIF2 in kidney cancer, but in no other cancer examined to date. In fact, in most cancers, HIF downregulates cyclin D1, but in kidney cancer, it upregulates cyclin D1, which is part of the puzzle, I'm sure, of why VHL patients get kidney cancer and not, for example, lung cancer, breast cancer, colon cancer. So just to show you how beautifully this works, so here's a series of Western blots. where the cells got a control guide or 2 different CRISPR-A guides for cyclin D1. So now we're going to treat with vehicle or the HIF2 inhibitor. So if we do a Western blot for cyclin D1, as expected when you come in with the HIF2 inhibitor, you downregulate cyclin D1. But notice with the cyclin D1 guides, we sustain or maintain the expression of cyclin D1. Now this is specific because NDRG1 is another well-studied HIF2 target gene, and you can see that, as you would expect, the cyclin D1 CRISPR-A guides have no effect on that HIF2 target gene. So in low throughput validation experiments, Nitin confirmed that cyclin D1 expression actually confers resistance, so I apologize for this busy slide, but here are the cells that got DMSO, here are the cells that got the HIF2 inhibitor, and here are the cells that got the HIF2 inhibitor, but where we artificially maintained the expression of cyclin D1. So we think there's an analogy to be made here because in human breast cancer, at least of the hormone responsive type, it's the estrogen receptor that's driving the expression of cyclin D1, and a mainstay of medical treatment for hormone responsive breast cancer is to combine an ER inhibitor, such as tamoxifen, with a CDK4/6 inhibitor, because of course CDK4 and 6 are the catalytic partners for cyclin D1. So based on this analogy, and we have some preclinical data in support of this, it might be a good idea to combine a HIF2 inhibitor with a CDK4/6 inhibitor in a clinical trial to ask this question is ongoing. But as sometimes happens, and maybe I'll even say as often happens, it turned out the control arm was more interesting than the experimental arm, which is one of the dozen reasons why it's good to do control. So I wish I could tell you I was smart enough to have anticipated this, but I was not. So here are the DMSO treated cells. So if you now look in the DMSO treated cells, and again, fitness advantage is over here. So these are genes that when are activated confer a fitness advantage in kidney cancer, and these are having the opposite effect. So right off the bat, if you look carefully, here's MYC. And MYC, as it turns out, is on a small amplicon in kidney cancer on chromosome 8. So this is kind of validating that, MYC is a good thing if you're a kidney cancer. But also over here is a less famous gene called SQSTM1. And SQSTM1 has several activities, but one of which is to activate NRF2, the NRF2 transcription factor. But the formal name for NRF2 is NFE2L2. But that's basically NRF2 to you or me. Now, the reason we like this is using horse and buggy technology about 10 years ago. We studied the most common amplicon in kidney cancer, which is an amplicon involving 5q, where there are about 60 genes. And again, using horse and buggy technology, we thought SQSTM1 was probably the target, but we didn't have anything like CRISPR-A. But in this CRISPR-A experiment, again, SQSTM1 seems to be the right gene. Moreover, if you go back to these guys turn out to be really interesting because these are genes that, when activated, confer a fitness disadvantage. And if you ask where some of those genes live, some of these genes live in regions of the genome where there's been a copy number reduction. And this gets to something that has been of interest, I think, to many cancer geneticists for years. So I talked about a Knudsen 2 hit tumor suppressor gene. Those are simple. You've lost one copy, you mutate the other. But there are many regions of the genome where, as best we can tell, there are no Knudsen 2 hit tumor suppressors, but you've lost maybe a chromosomal arm. And so the assumption is that maybe through dosage reduction, you've allowed a fitness advantage. And so these have been thought of as maybe being haploinsufficient tumor suppressors. So you start off being diploid, and maybe your expression is here. You lose a chromosomal arm, or maybe in some cases the entire chromosome, the expression goes down. But now with CRISPR-A, we can artificially reactivate those genes. And it's turning out this is a very useful technology for nominating haploinsufficient tumor suppressors on these missing chromosomal regions. So now I'm going to completely shift gears. And another observation about kidney cancer is it's been thought for decades to be highly immunogenic. It sometimes undergoes spontaneous remissions. It's characterized by a high level of T-cell infiltration. In the old days, some patients were cured with therapies like high-dose interleukin-2, although it was so toxic it sometimes also put patients in the ICU. And then sometimes these patients also respond to immune checkpoint blockade. So we, like many other people, have wondered, why should kidney cancer be so conspicuously immunogenic? And for starters, this is a fairly famous slide that many of you have probably seen. This is showing you mutational burden across cancer. So the y-axis is a measure of mutational burden. And here we have the names of various tumor types. And melanoma, you might know, is the 800-pound gorilla, presumably because of UV light. And so it's thought maybe that's one of the reasons why these tumors respond nicely to immune checkpoint blockade. But clear cell renal cell carcinoma is right in the middle. So there's nothing conspicuous about clear cell renal cell carcinoma. So what might be going on here? Well, we think a wildly underappreciated clinical experiment, despite parenthetically being published in the New England Journal, was a study done by Richard Childs and co-workers. So what they did out of sheer desperation, and I've spoken to him about this, it was just sheer desperation, they treated 74 patients with metastatic renal cell carcinoma with allogeneic stem cell transplants as a source of T cells, full stop. So in that study, about half the patients responded and about 11 or 12% had durable complete responses. And in one of the patients who had a durable complete response, they found donor T cells that were reacting with an endogenous retrovirally derived peptide on the surface of the tumor. And they never found expression of this endogenous retrovirus in normal tissues or other cancers. It seemed to be restricted to renal cell carcinoma. Moreover, some groups, but I would admit not all groups, have suggested that the expression of endogenous retroviruses in kidney cancers at least correlates with the likelihood that you're going to respond to immune checkpoint blockades such as anti-PD-1 that you heard about earlier. Now, in the case of the Richard Childs ERV, his group very nicely showed that this ERV was under the control of HIF2, which would explain very nicely why it was upregulated in kidney cancer, because I've just told you about HIF2 being the signature driver in kidney cancer. So Qianqin Jiang in my lab wanted to know, was this a unicorn, never to be seen again, like really great for that patient, but good for them, never to be seen again, or was this the tip of the iceberg and we should have been paying a little bit more attention? So what Qianqin set out to do was to test two hypotheses. One, first hypothesis was that HIF drives the expression of multiple ERVs with the Richard Childs ERV, which has now been renamed ERVE4, and the nomenclature here is horrible, I apologize. So she thought maybe HIF actually drives the expression of multiple ERVs, and maybe some of these other ERVs, like the Richard Childs ERV, are translated into peptides that can then be displayed on the cell surface. So to address the first question, Qianqin took a renal carcinoma cell line that's VHL defective, and she effectively generated 3 isogenic pairs where HIF2 would be high or HIF2 would be low. So for example, one thing she did was she restored the function of the VHL gene by stable infection, or she treated the cells with DMSO or that HIF2 inhibitor, or she knocked out HIF2 alpha with a CRISPR guide, which you can do at least in the short term in these cells if you keep them under high serum. So now she has 3 isogenic pairs, high HIF2, low HIF2, and we do RNA-seq. And then with our colleagues, David Brown and Kathy Wu, we're just going to look at about 3,000 annotated ERVs where the ERVs are relatively intact, and you could imagine in your wildest dreams them being transcribed and translated into peptides. So we're not looking at every LTR, we're not looking at every line element, we're just looking at about 3,000 ERVs that are relatively intact. So here are the Venn diagrams from the RNA-seq experiment. So let's, for today, just be uber stringent, and we're only going to look at the 15 ERVs that scored in all 3 comparisons, although I'll tell you most of the double headers are true positives also. And we're also using fairly stringent cutoffs in terms of the fold induction. So here are the 15 that scored in all 3 pairwise comparisons. Now again, for the students, it's always nice to have an internal control, even if you didn't know you had an internal control. So the internal control here was we rediscovered the Richard Childs ERV. So that was very satisfying that we rediscovered the Richard Childs ERV. We also rediscovered one of the ERVs that was in one of those JCI papers I showed you as a predictive biomarker for immune checkpoint blockade. So then we thought maybe we're really onto something. So then we did ChIP-seq, and we did ChIP-seq also several different ways. So one way we did it was to use a HIF2 alpha antibody in those cells where we did or did not knock out HIF2 alpha. But again, one thing I've learned is it's always nice to have multiple ways of doing something. So if I only had those first 2 tracks, I think most of you would have been unimpressed by this HIF2 binding site. And parenthetically, here's the Richard Childs ERV. I should have said that. So here's the Richard Childs ERV. Here's a little blip in the HIF2 ChIP-seq. But Nitin Shiroli in my lab had already knocked in a flag HA tag into the endogenous HIF2 alpha locus in multiple renal-carcinoma cell lines. So that allowed us to do ChIP-seq in multiple renal-carcinoma cell lines with a flag antibody. And now you can see this was really a true peak. In fact, Richard Childs had nominated a HIP binding site on the shoulder there, but I think you can see it's actually over to the left, not that that really matters. But here are a couple of the new ERVs we've discovered. So again, I'm showing you at the top the ERV, and I picked two ERVs that actually, they're perfect bookend HIF2 binding sites. So here's one, here's the other. So now you start to think maybe there are other ERVs under HIF2 control. So then, to begin to address whether some of these are transcribed and translated, we did polysome-seq with Sterling Churchman, again, probably using ridiculously stringent cutoffs. But here again, the Richard Childs ERV scores, as does those two ERVs that were bookended with the HIF2 binding sites. And then with the help of Carl Klauser at the Broad Institute, we've been doing HLA mass spec on cell lines as well as tumors. This is very much a work in progress, but I will tell you, for example, we've now looked at 11 kidney tumors, and for 11 of those, and for 6 of those 11, we had normal tissues. And so I think we're now up to about 30 different ERV-derived peptides that are on the cell surface of these kidney tumors. And in every case where we had normal tissue, it was not on the normal tissue, it was just on the kidney tumor. And I'm sure most of you are aware that your HLA allele type dictates which peptide you can or cannot present. So we're imagining in time generating a lookup table where you'll look for the HLA type of the patient, and then you'll be able to predict which of these peptides will be on your cell surface. Okay, switch gears again. I think another hot area, and this has been touched upon today, is, what do we do with these genetically validated but otherwise undruggable targets in cancer? So there are many things you could think about, but here are 4. Frankly, I already touched upon examples, or an example of these first 2. So, loss of VHL. Classically, that would be viewed as undruggable, but we exploited sort of an epistatic relationship that you lose VHL, but you're now being driven by HIF2. And then I already told you that the HIF2 inhibitor was an allosteric inhibitor. I've had a long-standing interest in exploiting synthetic lethal interactions, and that came up today. But I want to talk to you briefly about small molecule degraders. But again, this is a big problem, I think, in cancer therapeutics. I mean, this is a partial list of, I think, genetically validated but undruggable targets in cancer, although I'm hopeful that RAS will leave this list now in the next year based on some of the pioneering work that we're reading about. So in terms of degraders, our lab and Ben Ebert's lab working in parallel discovered that the thalidomide-like drugs act as molecular glues that reprogram a ubiquitin ligase, in this case the cereblon ubiquitin ligase, to now mark for destruction 2 otherwise undruggable transcription factors called IKZF1 and IKZF3, which turn out to be near and dear to the hearts of multiple myeloma cells. And once this was discovered, almost immediately Craig Crews and Jay Bradner said, well, if that's how the IMiDs work, we can start playing chemically with the IMiDs so that maybe they'll recruit other targets. But in fairness, this really goes back to an idea of Ray Deshays and Craig Crews many years ago, the idea being maybe you could design bifunctional chemicals that would recruit an E3 ligase to now earmark a target for destruction. And so in the field, these are sometimes referred to as PROTACs. These are sometimes referred to as molecular glues, and these are sometimes referred to as degranamids. And I should point out that part of the excitement about the IMiD-like molecules is that the molecular glues are much more drug-like than these PROTACs, which tend to be relatively big and clunky. But if you think about it, there are lots of ways a small molecule might affect the stability of a protein, because protein stability is highly, highly regulated in cells. For example, there are about 500 ubiquitin ligases. They're opposed by 100 DUBs. The ability of those ligases to recognize their targets is often influenced by post-translational modifications, protein folding, protein-protein interactions, subcellular localization. So it's not a leap to imagine that there would be other ways that a small molecule might degrade or destabilize your favorite undruggable proteins. So knowing full well that the biotech industry and pharma were going to run with the IMID paradigm, which they have, we thought maybe as academics we should step back and see if there are other ways to discover other types of chemical matter that would degrade proteins. And one of the mantras in my lab is up assays usually beat down assays, something I learned from my friends in pharma 20 years ago. So why do people who like to do chemical screens and genetic screens also almost invariably gravitate towards up assays? And it turns out there are two simple reasons. One is that up assays usually have better signal-to-noise characteristics because it's easier to see a positive in a sea of negatives than a negative in a sea of positives, which is, for example, what makes astronomy possible. But more importantly, if you're going to do chemical screens and genetic screens, if you're doing a down assay where something complicated is now not happening quite as well or not happening at all, there's just a lot of trivial ways to make a complex system such as, a cancer cell work less well or work less effectively. So when you do a down screen, you always have this constant headwind of uninteresting, trivial stuff. That's just, a monkey in the, something where you've just taken a complex system and you're throwing a monkey wrench at it. And we just don't want, we're not interested in that stuff. We want stuff that's specific and interesting. And so to design an up assay for protein degraders, Sagar Kaduri in the lab made a reporter where the protein of interest is fused to a modified cytidine kinase that can take a non-natural nucleoside, BVDU, and convert it into a toxin. There's a little spacer, there's a V5 tag, and then to make sure the cells retain the reporter off the same transcript as a GFP. So now the idea is you add a chemical or genetic perturbant, you add BVDU, and you look for green survivors. So in a proof of concept experiment, Sagar made cells that have the IMID target IKZF1 fused to CK. He grew them in 384 well plate assays, and then to each well added a different annotated chemical. And I hope you can see in the back of the room there are three positives. So these two wells got the IMID pomalidomide, and this well turns out to be an assay positive because this chemical simply interferes with BVDU uptake. So then Sagar screened an annotated chemical compound library. The top plate is the IKZF1 fusion. The bottom plate is unfused CK. The outer columns here are just some controls, so we can ignore those. And then otherwise, each row has two different chemicals at 10 different concentrations. So here, for example, is an assay positive that's scoring at the highest concentration in both plates, so we don't care about that. This is what a true positive looks like. So this is a true positive called Spalgin-1 that in secondary assays does degrade IKZF1. And parenthetically, unlike the IMIDs, it doesn't require cereblon, which some people might find interesting because loss of cereblon is one way to get resistant to the IMID-like drugs. There may be a couple of people in the audience who know that Spalgin-1 was originally described as an autophagy regulator, but that's sort of a red herring here. So we kind of like this assay. Not shown here, the other advantage of an up assay is you can actually do pooled screens with CRISPR libraries, and we've had some fun with that, identifying genes that when inactivated destabilize your favorite protein. But we also realized that as an up assay, it really lent itself to revisiting natural product collections. So I know, again, not to offend the chemist, but there's no human chemist I've ever met who can match nature for structural diversity when it comes to chemistry. And so the pros of screening natural products is enhanced chemical diversity. And frequently, when you get a natural product hit, it's often pretty drug-like right out of the gate, especially if you're doing a cell-based phenotypic screen. The con, however, is that contaminating toxins cause false positives in down assays. But again, we're not doing a down assay. And false negatives in up assays, but I'm going to show you how we got around that. It can be difficult to isolate and identify the active chemicals in the mixtures that score as hits, but I'm going to show you how we got around that. And it also can be difficult to identify the direct protein target of the natural product, but there's some really powerful genetic and biochemical approaches to that problem that I don't have time to talk about today. So this is the work of Matt Boudreau, a very talented chemist who came to my lab to work on this. And he decided to set out to find degraders of the famous beta-catenin, another undruggable oncoprotein. So we're collaborating with a fantastic group led by Barry O'Keefe at the National Cancer Institute who I think has come up with a really clever version of natural product screening, which really married very well with our UP assay. So what Barry and his team decided to do was to take the over 230,000 natural product mixtures at the National Cancer Institute. These are broths, extracts of almost everything that's ever grown or slithered around the world. And by the way, your tax dollars paid for these, so you might as well request this library too. So he took this collection, this amazing collection of 230,000 extracts, and they realized that if they just ran these extracts over a single column, such that each mixture is now represented by 7 or 8 fractions. First of all, you've dramatically simplified the mixtures. Secondly, maybe you've now separated that noxious thing from the interesting thing. Moreover, and I wouldn't know how to do this, but I bet Brent would know how to do this, they chose their columns specifically so it removes a lot of the nuisance columns. Now I am speaking New York fast. It removes a lot of the nuisance chemicals that typically plague phenotypic screens with natural products. So we get a 2 for her. We're going to simplify the extracts, and we're going to remove, hopefully, a lot of the uninteresting chemical matter that often plague phenotypic screens. There's some other verbiage here about some of the other advantages, but we don't have time to go through this today. So what does this actually look like? So Matt's now screened over 200,000 extracts, actually. And he's looking again for beta-catenin degraders, and he counter-screens with the unfused CK. And so using his cutoffs, he has about 400 hits. And I'll just show you in real life what one of these true positives look like. So the Z-score here is a measure of living green cells. And again, that's our UP assay, living green cells. And so in hindsight, you can see this extract probably did have a positive. If you look at this red, which was the beta-catenin fusion cells versus the unfused CK cells. But, you know, if we had used this as our cutoff, we would have had too many hits. Our cutoff is much higher. So this did not score. However, if you now look at the subfractions, you can see that V5 and V6 are positive. So I think you needed to be a 3 to be a positive. And so V5 and V6 are the true positives, and I don't have time to show you, but these do validate as being beta-catenin degraders. And I'll also point out, and I see Brent nodding his head, we also take comfort when we have 2 adjacent fractions that are scoring, because again, it's just simply a single column fractionation at this point. So this is what we often see is 2 adjacent fractions both scoring. Now, Ben Lampson, a very talented physician scientist in my lab, said, hey, I like these UP assays, and I like this suicide gene cassette you're using, so can I use that too? And his interest is in lymphoma. And so what he decided to do was to place the suicide gene under the control of an NF-kappa B responsive promoter. The control is a constitutive promoter. And again, he's doing an iris GFP trick. And so the idea here was to treat the cells with LPS, the NF-kappa B agonist, LPS, which will turn on the expression of the suicide gene. And now he's going to do, dare I call it, an old-fashioned CRISPR cut or CRISPR inactivation screen. It's been all of 18 to 24 months. Can I call it old-fashioned now? So we're going to do an old-fashioned CRISPR inactivation screen and look for genes that, when inactivated, prevent the signaling by LPS to NF-kappa B. So this worked far better than I thought it was going to work. So, hold on. Well, that's good. So here are the data from the NF-kappa B screen. So in red are the top scoring genes. So again, these are genes that, when inactivated, prevent NF-kappa B signaling. And so if I'm going to blow those up over here, and we'll return to those in a minute. Whereas in the constitutive promoter, really the top scoring gene were the guides against CK itself, the suicide gene cassette. So if you look at these genes in red, and again, these are genes that when they're inactivated, prevent signaling by LPS to NF-kappa B. So in one experiment, we got 20 years worth of NF-kappa B biology. So if you had not known, for example, that the receptor for LPS was TLR4, TLR4 was one of the top scoring hits, and we got the entire signal transduction cascade all the way to NF-kappa B itself. So all of this is to say this is another powerful, I think, technology that you might want to think about. But of course, you don't do these sorts of screens to only rediscover what was known, so you hope you find some things that are new. And so, let's see if we can, so here's one thing that was new, CCDC 34, or whatever it is, CCDC 134, an anonymous gene that has been understudied, but maybe more interestingly, there's another gene there, STT3A. So I bet no one here has heard about STT3A. STT3A is an enzyme that lives in the endoplasmic reticulum where it glycosylates certain proteins that are destined for the cell surface, and it's known that TLR4 has to be glycosylated to get to the cell surface. So here's some low throughput validation experiments. So here you're looking at an H8 tag version of TLR4, and when it's glycosylated, you see this electrophoretic mobility shift. So if you knock out STT3A or this orphan gene, now TLR4 does not get glycosylated. And by the way, here's where it's really important that this is an upscreen, because this is not just some housekeeping function, and in particular, the paralog STT3B didn't score here. This is something unique to STT3A. And for good measure, here's a positive control, since it was known that HSP90B1 was required for the glycosylation of TLR4. So then we got a tool compound from Joe Contessa at Yale that blocks or inhibits STT3A, 3B, and who knows what else. So here at low micromolar concentrations, the tool compound blocks the glycosylation of TLR4. And I'll remind you that the cells, the reporter cells, also express GFP under the control of NF-kappa B. So when you give the cells LPS, the cells go green, and when you treat with the inhibitor, they go dim. And so again, you know, Eureka, high five, this is figure 6F and G, I guess, or whatever, and maybe I could just write my paper now. But these are both down assays, right? So this is a down assay, you're blocking glycosylation. This is a down assay, you're blocking GFP expression. How would you know this is on target? How would you know this is specific? And frankly, here, no one delivered on a silver platter a drug-resistant mutant to us to say, here's your control. Here's the drug-resistant mutant the way they had with HIF2. And I didn't plan this. I didn't know this was going to be one of the themes for today. But we decided to use CRISPR-A, which are now all world's experts on CRISPR-A after today's. And so I'm just going to add, one more wrinkle here. So again, as you heard, this is based on the technology developed by David Liu and John Dench and colleagues. We're actually using two different versions. So you heard about this, but the idea is you have a nuclease dead Cas9, and we're going to fuse to one of two different mutagenic enzymes. One causes those C to T changes you heard about, and one causes an A to G change. So you introduce a Cas9 that's going to be mutagenic, and now you have a custom sgRNA library for your gene of interest, which in our case is STT3A. So the idea was you add the library, you treat with DMSO or the Joe Contessa tool compound, add LPS, and now you do FACS to sort for the persistently bright cells, even in the face of the inhibitor, as though those cells might have an STT3A that's resistant to the drug. And again, I remind you that there's a GFP reporter linked to NF-kappa B. So here what the data look like. I'm sorry, this is quite busy. Suffice it to say, here's the A to G base editor screen, C to T base editor screen. Here are some controls we can ignore. And then we're going to tile across the gene with guides. And here I'm showing you STT3A, and I'm showing the position of the guides based on the codons in the STT3A open reading frame. So a 0 means the guide was neither enriched nor depleted. But what you're looking for are guides that were enriched in the bright cells, because you're hoping those are going to induce drug resistance. Now, the algorithms for predicting the actual mutation that will be induced by that combination of guide and mutagenic Cas9, they're very, very good. They're about 90% accurate, but you still have to do low throughput experiments to validate exactly what mutations the guide could induce. So here's one of the A to G base editor hits, and it was capable of inducing several different mutations. This was one of the C to T base editor hits. It could induce that mutation. And then in low throughput experiments, you show or ask whether these really do confer resistance. So I apologize for this busy slide, but in the lower left, we're looking at cell surface TLR4. So here you see TLR4 on the cell surface until you come in with the STT3A inhibitor. But if now in orange, green, or blue, you introduce some of these putative drug-resistant mutants, now TLR4 gets back to the cell surface. And if you don't like that assay, here's the equivalent assay looking for restored glycosylation
of TLR4. So you can see that the drug-resistant variants over here likewise are drug-resistant as measured by restored glycosylation of STT3A. So I just want to echo what you heard earlier. I think this is a game-changing technology. It's just so powerful when you can once and for all say, this is on target and this is, I'm not fooling myself. And in this case, it was quite gratifying because I'm new to this field. And when I started describing this work to people in the field, they said, oh, that compound? We're not even sure that compound binds directly. Oh, that's a terrible compound. No one would use that compound. And I said, I have genetic proof that it's binding directly to STT3A. And by the way, all you structural biologists who gave up on solving the structure of the drug, I will tell you where it's binding. I will tell you the residues that are touching the drug. So fortunately, Kasper Locher and Anna Ramirez in Switzerland said, okay, we'll take the bait. So they revisited doing the structure with a few tweaks, and lo and behold, the drug binds right to the enzyme, and our screen had already predicted exactly which residues were touching the drug. So in closing, I showed you this before, and I apologize, I think we started a little bit late, but we're almost home free now. So I showed you this. The drug did go into phase 3 testing. The phase 3 testing was positive. It was reported at ESMO actually this week, so we're hoping the drug will be approved for sporadic kidney cancer. But another truism in medical oncology is that most drugs work better in the frontline setting than they do in very late lines of therapy. So we were able to convince Peloton and then Merck to treat 61 patients with von Hippel-Lindau disease who had measurable kidney tumors that had never been treated medically before. Instead, these people, they develop so many tumors of so many organs. They're often in careful surveillance programs where they'll get an MRI every 3 to 4 months. And they'll only be treated, and that often means going to the operating room, if the tumor exceeds a certain size or it changes its growth kinetics. So this was sort of a pseudo frontline experiment. And so here you're looking at the 61 patients with von Hippel-Lindau disease. Here, again, are swimmer's plots, but once again, this is 1 year on therapy. And you can see that most of the patients were doing well, even out beyond 3 years. If you don't like swimmer's plots, here are the waterfall plots showing the indicator kidney tumor shrinking in response to therapy. So I'm a lumper rather than a splitter, so I would say all of the tumors got at least somewhat smaller. But if you're a RECIST fan, I think currently the RECIST rate is about 64%. The other bonus here was these patients often had incidental tumors of their eye, brain, spinal cord, pancreas. So here are the central nervous system hemangioblastomas shrinking. Here are they also developed a tumor called PNET, which is a neuroendocrine tumor of the pancreas. You can see almost all those tumors responded, including some complete responders. And particularly gratifyingly, these patients, as I said, were in surveillance programs. So here in gray is the 4 years of observation before going on the drug in green. And every place you see a dot or a circle or a diamond, they're going back to the operating room to have yet another tumor removed. And you can see once they went on the drug, the operations almost completely stopped. And so the FDA took the extraordinary measure of approving the drug simply based on a phase 2 trial experience. But I will end by saying I've been an oncologist in my earlier life, and now I'm a cancer biologist, and I know we look at a lot of clinical data, and it's just so easy to forget that with every bar or triangle or asterisk, whatever it is, there's an actual human being attached to it. And so just to kind of leave with sort of a human face to this, almost immediately the VHL patients on the trial started posting on their social media websites that they were responding to the drug. And you can imagine these people have had this sort of Damocles over their neck for their entire life, and they've seen this disease ravage their family generation after generation after generation. So here's a patient, for example, saying, I never thought I'd see this day. And they're describing that their tumors were getting smaller, were stable, or in some cases had disappeared entirely. And since everyone likes a movie, here's a vlog that was sent to me. I didn't know what a vlog was when this was sent to me, but I asked my kids. And I do have permission to show this patient's face.
Hey, it's Justin. I just wanted to give you a quick update. I am in a gondola right now in Taiwan. Over there is Taipei 101. The gondola is actually right by the Taipei Zoo. But I just wanted to give you a quick update and say I'm doing well. I'm enjoying my trip. If it wasn't for the PT2977 drug trial, I would have never been able to come out here and do what I'm doing right now. So I just want to thank Peloton, and I hope Merck will fast track this drug for a VHL treatment. So if you guys are listening, hopefully you guys will put it on the market to help VHL. But yeah, keep watching these videos. I'll be making more, and I'll get better at it, and I have to get the angles right because I kind of look fat, you know?
Yeah, I love that because that to me said he was back to his pre-morbid state where his biggest concern was whether he's going to look fat on his vlog and not, you know, deathly concerned about what his next MRI was going to look like. So with that, thank you very much for your attention. Thank you for...
Mm-hmm. You kind of reminded me a little bit about, you may have heard of AlphaFold, that was recently released. They kind of can use genetic sequence to predict proteins' 3D structure and extension. Is this at all like kind of similar? So you mentioned that it can be used to, you mentioned that HLA was used to be able to inform what genes to specifically target through CRISPR. So is there any kind of overlap between these two technologies and how those can inform what therapeutics can be made?
Yeah, that's actually a spectacular question, and I applaud you for asking it, because I would not have been sophisticated enough to ask such a question when I was an undergraduate. You're absolutely right. So in addition to empirically determining which peptides can bind to which HLA types, there are lots of efforts to actually predict computationally which peptides are likely to be immunogenic and which peptides can be displayed by which HLA alleles and or, you know, products, and maybe people in this room who do that kind of work. So I think both things are happening simultaneously. The biochemical tools are getting better, but the computational tools are getting better. So it might be in time this could all be done in silico, and you'll just be able to predict what the peptide will be and which HLA type would be relevant.
So is there a relationship between your ERP story, between exposure to hypoxia and activation of these endogenous viral elements?
Yeah, it's a very good question. So I don't know the answer. So is this just fortuitous that there's so many ERVs that have neighboring HIF sites? Is it all by chance, or is there some deeper biological truth that we simply haven't figured out? We certainly haven't figured it out if there is a deeper biological truth. But I can imagine that we know for sure that mammalian embryogenesis occurs under a hypoxic condition. The intrauterine environment is hypoxic. So there are certain regions of the genome that'll be open, including genes that are regulated by HIF, and maybe that facilitates where ERVs are going to integrate because the chromatin is more open. But I haven't come up with a better teleological argument. You may know that, again, there are people who study the crosstalk between ERV, regulatory elements, and oncogenes, and vice versa, and so we're still trying to figure that out.
Yes, really great stuff. So I'm wondering about the natural products. Really interesting approach, and the struggle we've always had is it's two things: resourcing them,
Yep.
and then as we start figuring out mechanism. And I'm curious if you have ideas about that.
So for the second part of it, which is finding the target, the technique I'm very impressed with is the technique that was developed by Tarun Kapoor at the Rockefeller and refined further by Deepak Nishawan at UT Southwestern, which leverages cell lines that have mismatch repair defects, so the genome gets riddled with point mutations, and then the idea is to go in, treat with the compound, and if you have the right screen where you can, hopefully in a positive selection way, get the drug-resistant clones, you can then do whole genome sequencing, and frequently what they find, not surprisingly, is recurrent mutations in the actual direct target of the drug. So if we get hits from our screen, I've already talked to Deepak, who I've known for many years, about using his platform to try to find the targets. The first problem, I think, is a problem depending on the synthetic challenges of making of synthesizing the compound versus growing up vats and vats and vats of yeast or E. coli. or whatever. But I'm also working with a company called LifeMine Therapeutics, where I'm going to have financial conflict of interest. And it turns out there have been great strides, at least in fungi, being able to bioinformatically identify the various genes that are responsible for the production of natural products and predicting what the products would be, and then re-engineering the fungi to be far better producers of that particular natural product. So depending on the source, maybe we could re-engineer the host to be a better producer and do it that way. Using CRISPR-A, for example.
Bill, in the, one of the volcano plots,
Yes.
it was a HIF2 alpha inhibition. I noted that MDM2
Yeah.
is the most,
Yeah.
Carol's favorite. And so,
I should have known. I should have known. Yeah.
Just in vitro, at least, if you treat with an MDM2 inhibitor, is there a beneficial?
Yeah, it's a great question, and this is a little embarrassing. So when we published our initial paper showing that the HIF2 inhibitor was so active in preclinical models, based on a really limited number of cell lines, we stuck our neck out and said we think P53 is going to be important here. And it turned out one of the lines of evidence was we had a cell line in the lab that had a P53 mutation, and it had a P53 mutation because I had a very sloppy postdoc who never changed the media in his cells, and I'd go in and the media would look like Mountain Dew, and you could hear the cells screaming. And then after a couple of years of this, they acquired a P53 mutation. So they had a P53 mutation. They were resistant to the drug, but again, I caution students, that could be true, and unrelated. So later, using tools like CRISPR, we satisfied ourselves that it wasn't actually P53. In fact, you could CRISPR out P53, and the cells, were still sensitive. So so we were really surprised when MDM2 scored, because we had just convinced ourselves it wasn't about P53. So I'm hoping and thinking it's actually some other substrate other than P53 that's important there, but we are revisiting that. I'm sorry, Carol. Yeah.
There are other questions or comments? Thanks again.
Okay, thank you.